what if the key to time travel isn't hidden in the grandeur of massive spaceships or the elegant, theoretical curves of a wormhole, but in a realm so small, so counterintuitive, that it forces us to question the very fabric of reality? A world where particles can be in two places at once, where they defy our expectations of cause and effect, and where they can communicate instantaneously across vast cosmic distances. Welcome to the quantum realm, the strange and beautiful foundation of modern physics, and perhaps our most promising path to unlocking the profound mysteries of time itself. Quantum physics is not just a theory about the bizarre behavior of the tiniest constituents of matter. It is a field that is teeming with possibilities, with phenomena so complex and so contrary to our everyday experience that they have fundamentally reshaped how we think about space, about matter, and most tantalizingly, about time. Have you heard of quantum entanglement? The spooky action at a distance where two particles can remain mysteriously connected, their fates intertwined, no matter how far apart they are. Or have you contemplated the strange implications of retrocausality? The mind-bending idea that a choice made in the future could ripple backwards to influence an event in the past. These are not just concepts from the pages of science fiction. They are active areas of scientific inquiry, ideas that are pushing the boundaries of our understanding and hinting at the familiar linear rules of time we have always taken for granted might be just one limited perspective on a much deeper and far stranger reality. But time is not just an abstract scientific concept. It is the very rhythm of our lives, the relentless, forward-moving current that carries us from one moment to the next. Or does it? Could there be ways to slow it down, to speed it up, or even, perhaps, to reverse its flow entirely? The quantum realm, with its inherent uncertainty and its defiance of classical logic, introduces us to a world of bizarre and thrilling possibilities, from the potential to manipulate the very fabric of space-time to the exploration of alternate parallel realities. If you are ready to uncover how the strangest science of today could define the future of our relationship with time, then you are in for an exciting exploration. Together, we will break down the quantum mysteries that are reshaping our understanding of the universe, and we will venture into the incredible possibilities they offer. Welcome to this fascinating journey into the heart of quantum physics and the tantalizing dream of time travel. Time, as we experience it in the course of our lives, feels like a simple and straightforward concept. It is the steady, metronomic beat of an alarm clock that rouses us from sleep, the relentless ticking of seconds that turn into minutes, and minutes that turn into days. It is a seamless, linear progression, a universal ruler that we use to structure our existence, to measure our past, and to plan our future. But this intuitive, everyday experience of time as a steady and absolute march forward is a powerful illusion, a macroscopic simplification of a much more complex, more fluid, and more mysterious reality. To truly begin an exploration of time, we must first understand how our scientific conception of it has evolved. The classical view, most famously articulated by Isaac Newton, treated time as an absolute and universal constant. In the Newtonian universe, a single, master clock ticked at the same, unwavering rate for every object, in every corner of the cosmos. It was a fixed, unchanging background, a rigid stage upon which the drama of motion and force played out. But this comforting, clockwork picture of the universe was shattered in the early 20th century by Albert Einstein's theory of relativity. Einstein revealed that time is not absolute. It is relative. It is a dynamic and flexible dimension, inextricably woven together with space into a single, four-dimensional continuum called space-time. And this fabric of space-time is not a passive stage. It is an active participant in the cosmic drama, capable of being stretched, compressed, and warped by the presence of mass and energy. This warping of space-time is what we experience as the force of gravity. Time, in this relativistic picture, is a local phenomenon. The closer you are to a massive object, like a planet or a star, the more space-time is curved and the slower time flows. An atomic clock on a mountaintop will tick slightly faster than an identical clock at sea level. The astronauts on the International Space Station are aging a tiny fraction of a second slower than we are here on Earth. This effect, known as gravitational time dilation, is real and measurable. Similarly, the faster you move through space, the slower you move through time, a phenomenon known as velocity time dilation. A spaceship traveling at near the speed of light would experience time passing much more slowly than a stationary observer. For the astronauts on board, a journey that takes a few years could correspond to centuries or even millennia passing on Earth. Relativity revolutionized our understanding of time, transforming it from an absolute, universal constant into a dynamic, malleable dimension, intimately tied to the geometry of space and the motion of objects within it. But even this groundbreaking, relativistic view of time is now being challenged and deepened by the strange and often baffling world of quantum mechanics. Quantum mechanics throws a new and powerful wrench into our understanding of time, revealing a reality that is even more counterintuitive than the curved space-time of Einstein. At its core, quantum mechanics is a theory of probabilities and possibilities, not of certainties and definitive outcomes. The quantum realm is a hazy, indeterminate world, and this inherent ambiguity extends to the very nature of time itself. One of the foundational principles of quantum mechanics is the uncertainty principle. We often think of this in terms of position and momentum, but there is also a corresponding time-energy uncertainty principle. This principle suggests that the more precisely you try to measure the energy of a quantum system, the less precisely you can know the duration of that state, and vice versa, at the most fundamental subatomic level. Time is not a sharp, well-defined coordinate, but a fuzzy, blurred, and uncertain quantity. It is as if the universe, at its smallest scales, refuses to be pinned down to a single, definite moment. Another, even more profound. Quantum concept is superposition. A quantum particle, like an electron, can exist in a superposition of multiple, seemingly contradictory states at the same time, as long as it is not being measured. This raises fascinating, if highly speculative, questions about the nature of time. If a particle can be in a superposition of different locations or different energy states, could it, in some sense, be in a superposition of different moments in time? Could different timelines or different temporal possibilities coexist in a quantum state until a measurement collapses them into a single, experienced reality? While this is far from a mainstream scientific theory, it is the kind of mind-bending question that the strangeness of the quantum world forces us to ask. These quantum peculiarities provide the fertile ground from which new and often radical theories of time are beginning to emerge. One such idea is the block universe theory. This is a concept that has its roots in relativity, but it gains a new and deeper resonance in the context of quantum mechanics. In the block universe view, time is not a flowing river that carries us from a fixed past to an open future. It is a static, four-dimensional block of space-time, in which all of time past, present, and future exists simultaneously and equally. Your birth. This very moment you are reading these words, and all the events of the distant future are all equally real, all just different coordinates in this frozen, four-dimensional landscape. In this picture, the flow of time is a subjective illusion of our consciousness, a trick of our perception as our awareness moves through this pre-existing block. Another, even more radical, idea is that time, as we perceive it, may not be a fundamental aspect of reality at all. It could be an emergent property, a macroscopic phenomenon that arises from the deeper, more fundamental, and perhaps timeless interactions of the quantum world, in the same way that temperature emerges from the collective motion of countless individual atoms. In this view, at the most fundamental level of reality, there may be no before or after, no arrow of time, only a complex network of quantum relationships. The time we experience is a kind of statistical thermodynamic illusion, a consequence of the fact that we are large, complex, and entropy-producing systems. Finally, the phenomenon of quantum entanglement, the spooky action at a distance where two particles can remain instantaneously connected across vast stretches of space, adds another layer of mystery to the quantum time conundrum. If this non-local connection can link particles across space, could a similar form of entanglement link events across time? Could a measurement made on a particle today be entangled with the state of a particle in the distant past or future? This is a highly speculative and controversial area of research, but it is one that is being actively explored by some theoretical physicists. It hints at a universe where the relationship between past, present, and future is far more complex and interconnected than our classical intuition would ever allow. From the uncertainty of quantum measurements to the timelessness of the block universe, from the emergent nature of time to the temporal possibilities of entanglement. Quantum mechanics is not just challenging the simple, classical view of time. It is shattering it. And from the pieces, it is offering us the tantalizing clues to a new, deeper, and far more wondrous understanding of this most fundamental and most mysterious aspect of our reality. Imagine, for a moment, a particle approaching a solid wall. In our everyday classical world, the outcome is simple. If the particle does not have enough energy to break through or go over the wall, it will bounce off. The wall is an absolute barrier, but in the strange and counterintuitive world of quantum mechanics, this is not always the case. There is a small but non-zero probability that the particle can simply appear on the other side of the wall without having broken it and without having had enough energy to overcome it. This is the phenomenon of quantum tunneling. And it is not science fiction. It is a real, measurable, and essential feature of our universe. At its core, quantum tunneling is a direct consequence of the wave-like nature of quantum particles. A particle, like an electron, is not a solid, point-like object. It is a wave function, a cloud of probability that describes the likelihood of finding the particle at different locations. This wave does not stop abruptly at an energy barrier. It decays exponentially into it. If the barrier is thin enough, the wave function can have a small, but non-zero amplitude on the other side. This means that there is a finite probability that the particle, when measured, will be found on the far side of the barrier. Having seemingly tunneled through an impossible obstacle, it is as if the particle has momentarily borrowed the energy needed to overcome the barrier, thanks to the energy-time uncertainty principle passed through, and then repaid the energy on the other side. This unsettling, yet mesmerizing, behavior is not just a theoretical curiosity. It is a process that is happening all around us, and even within us. The sun shines because of quantum tunneling. In the immense heat and pressure of the sun's core, hydrogen nuclei are constantly colliding. Classically, they do not have enough energy to overcome their mutual electrostatic repulsion and get close enough to fuse together. But thanks to quantum tunneling, they have a small chance of bypassing this energy barrier, allowing the strong nuclear force to take over and initiate the process of nuclear fusion. It is this quantum leap that powers the sun and, ultimately, all life on Earth. Quantum tunneling is also at the heart of much of our modern technology. The transistors that are the building blocks of every computer and smartphone rely on the ability of electrons to tunnel through thin, insulating barriers in semiconductor materials. The flash memory that stores our data works by trapping and releasing electrons in a floating gate through a quantum tunneling process. Even some biological processes, like the way enzymes catalyze chemical reactions or the way our sense of smell works, are now thought to involve a form of quantum tunneling. The stark difference between the behavior of the quantum world and the macroscopic world of our everyday experience is a matter of scale and probability. While a single electron has a small but significant chance of tunneling through a thin barrier, a macroscopic object, like a basketball or a human being, is a collection of trillions upon trillions of particles. The probability of all of those particles tunneling through a solid wall at the same time is so infinitesimally, vanishingly small that it is, for all practical purposes, 0. We will never see a person walk through a wall, not because it is forbidden by the laws of physics, but because the odds are so astronomically against it that it would not happen even once in the entire lifetime of the universe. This scale-dependent nature of quantum effects is one of the reasons why the quantum world seems so strange and alien to us. Our intuition has been shaped by our experience in the macroscopic world, a world where probabilities have averaged out to become near certainties. But at the fundamental level, the universe is a game of chance, a world of probabilities and possibilities. Now, this is where the conversation turns towards the truly speculative and mind-bending. If a particle can tunnel through a barrier in space, could it, or perhaps the information it carries, tunnel through a barrier in time? This is a thrilling question that has captured the imagination of physicists and science fiction writers alike. While the concept of temporal tunneling is not a well-established scientific theory, it is the kind of what-if question that the strangeness of quantum mechanics invites us to ask. Could a particle tunnel from the present moment to a moment in the future? Bypassing the intervening time, could the information about a future event tunnel back to the present, giving us a form of precognition? These are ideas that are on the very fringes of theoretical physics, and they lack any experimental evidence. But they are born from a deep recognition of the parallels between space and time in modern physics. In Einstein's Relativity, space and time are unified into a single, four-dimensional space-time. If quantum tunneling is possible in the spatial dimensions, it is not entirely illogical to ask if a similar phenomenon could be possible in the temporal dimension. For now, the boundary between science fact and science fiction remains clear. Quantum tunneling is a real, observed, and technologically crucial phenomenon that governs the behavior of particles in space. Its potential connection to time travel remains a purely hypothetical and deeply fascinating speculation. But the very existence of a phenomenon like quantum tunneling, a phenomenon that so profoundly violates our classical intuition, should give us a sense of humility. It is a powerful reminder that our everyday understanding of the world is a limited one, and that the universe, at its deepest level, operates according to a set of rules that are far stranger, more subtle, and more wondrous than we can yet fully comprehend. It is a call to keep questioning, to keep exploring, and to remain open to the possibility that the universe still holds secrets that could one day turn our most cherished scientific and philosophical assumptions on their head. Could a decision you make today ripple backwards through time to influence an event that has already happened? This is a question that seems to belong to the realm of paradox and fantasy. And yet, it is a question that physicists are forced to confront when they grapple with the strange and beautiful implications of delayed choice experiments in quantum mechanics. This is not about time travel in the classical sense of rewriting history. It is about something far more subtle and perhaps even more profound. It is about the strange and seemingly retroactive way in which our choices as observers appear to shape the reality of the quantum world. The story begins with the famous double-slit experiment. As we have seen, a single quantum particle, like a photon, will behave like a wave and create an interference pattern if we do not know which of the two slits it has passed through. But if we place a detector at one of the slits to gain this which path information, the photon behaves like a particle, and the interference pattern disappears. The act of measurement changes the outcome. In the 1970s, the brilliant and iconoclastic physicist John Archibald Wheeler proposed a thought experiment that took this strangeness to a whole new level. He asked, what if we delay the choice of whether or not to measure the which path information until after the photon has already passed through the slits? Imagine a setup where the photon has already gone through the double-slit barrier and is on its way to a detector screen. At the last possible moment, we can choose to either insert a set of detectors that will tell us which path the photon took, or to remove them and allow the interference pattern to form. Classical intuition would tell us that this choice should make no difference. The photon has already passed through the slits. Its behavior, whether wave-like or particle-like, should already be a fixed, historical fact. But this is not what happens. When Wheeler's thought experiment and its various more sophisticated versions have been carried out in real laboratories, the results have been consistently jaw-dropping. Even when the choice of measurement is made after the photon has passed through the slits, the outcome is the same. If the detectors are inserted, the photon is found to have behaved like a particle. If the detectors are removed, the photon is found to have behaved like a wave. It is as if the photon, in its journey, somehow knew what choice the experimenter was going to make in the future, and adjusted its past behavior accordingly. This is a result that is so counterintuitive that it can make one's head spin, but it is crucial to understand what it does, and does not mean. Delayed choice experiments do not imply that we can send information back in time, or that we can literally change the past. There is no paradox, no violation of causality. The trick lies in the subtle and holistic nature of quantum measurement. A quantum system, like our photon, is not a classical object with pre-existing properties. It is a wave function, a cloud of possibilities, and the reality we perceive is only defined in the context of the entire experimental setup, including the final act of measurement. The behavior of the photon is not an intrinsic property that it carries with it on its journey. Its waviness or particleness is a property of the whole system, of the relationship between the particle and the measuring device. To ask what the photon was doing before the final measurement is to ask a question that, from a quantum perspective, may not have a well-defined answer. As Wheeler himself famously put it, no elementary phenomenon is a real phenomenon until it is an observed phenomenon. The past at the quantum level is not a fixed and unchangeable record. It is an open, probabilistic story that is only finalized, only brought into being by the observations we make in the present. This is a profound and deeply unsettling idea. It challenges our most basic, classical understanding of time and causality. We are used to thinking of time as a linear sequence, where a cause in the past leads to an effect in the future, but the quantum world seems to hint at a more complex and more intertwined relationship between the past, the present, and the future. Some physicists, in trying to make sense of these results, have been led to entertain the radical idea of retrocausality, the notion that influences can, in some subtle quantum mechanical way, travel backwards in time. This is not about sending signals, but about a more fundamental, and as yet not fully understood, temporal symmetry in the laws of nature. The choices we make now may be part of a larger, self-consistent loop of causality that includes both the past and the future. But even without resorting to such radical ideas, the delayed choice experiment serves as a powerful reminder of the fundamental weirdness of the quantum world. It is a world where our common sense notions of reality, of locality, and of time itself break down. And this has practical implications. The deep understanding of quantum measurement that has come from grappling with these paradoxes is essential for the development of quantum technologies. Quantum computers, for example, are built on our ability to precisely control and manipulate the delicate, superpositional states of qubits. The delayed choice experiment is a powerful tool for probing the very nature of this quantum state, for understanding how it is created, how it evolves, and how it is collapsed by the act of measurement. It is a mind-bending exercise in quantum logic, to be sure. But it is also a testament to the power of human curiosity, to our relentless drive to ask the deepest questions, and to our willingness to follow the evidence, even when it leads us into a reality that is far stranger, more subtle, and more beautiful than our classical minds could have ever imagined. The delayed choice experiment reveals the strange, retroactive influence of observation on a quantum system. But what if we could go a step further? What if we could not just decide whether to observe, but could also decide to forget what we have observed? This is the tantalizing premise of the quantum eraser experiment, one of the most bewildering and philosophically profound concepts in all of quantum mechanics. It is an idea that seems to be pulled directly from the pages of a science fiction novel, an experiment where the simple act of erasing information seems to rewrite a reality that has already happened. The story begins, once again, with the double-slit experiment. We know that if we measure which slit a photon goes through, we gain which path information, and this act of measurement destroys the wave-like interference pattern. The photon behaves like a particle. The quantum eraser experiment asks a simple, but audacious, question: what if we could erase this which path information after we have recorded it? Could we bring the interference pattern back from the dead? The setup for a delayed choice quantum eraser experiment is ingenious and complex. It typically involves a source that produces pairs of entangled photons. These photons are linked in such a way that they are a single, unified quantum system, even if they travel in different directions. One photon, the signal photon, is sent towards a double-slit barrier and a detector screen. The other photon, the idler photon, is sent along a different path to a separate set of detectors. The clever part is that the path of the idler photon can be used to determine which slit its entangled partner, the signal photon, went through. So, by measuring the idler photon, we are, in effect, measuring the which path information of the signal photon, even without directly interacting with it. And as expected, when we do this, the signal photons hitting the screen do not show an interference pattern. They behave like particles. But now comes the eraser part. The experiment is set up in such a way that we can make a choice about what to do with the idler photon. We can either measure it in a way that reveals the which path information, or we can erase this information by sending the idler photon through a set of beam splitters that scrambles its path, making it impossible to know which slit its entangled partner went through. And here is the truly mind-bending twist. This choice of whether to erase the information can be made after the signal photon has already hit the detector screen. And when the experiment is performed, the results are stunning. If we look at the total pattern of all the signal photons on the screen, it is just a diffuse blob with no interference. But if we then look at our data and select only those signal photons whose entangled idler partners had their which path information erased, a beautiful, clear interference pattern magically reappears. It is as if the future act of erasing the information has reached back in time to influence the past behavior of the signal photons, causing them to act like waves. At first glance, this seems to be a clear violation of causality, a form of retroactive rewriting of history. But as with all quantum paradoxes, A closer look reveals a more subtle and even more profound truth. The quantum eraser does not actually allow us to change the past. The key lies in the process of post-selection and the nature of entanglement. The interference pattern is not visible in the raw, total data. It is only revealed when we correlate the data from the signal photons with the data from the idler photons. It is a hidden pattern, a ghostly correlation that is only brought to light when we have the information from both parts of the entangled system. The choice we make in the future about the idler photon does not change what has already happened at the signal detector. It simply changes the way we are able to sort and interpret that past data to reveal a hidden, pre-existing quantum correlation. The story is self-consistent across time. There is no paradox. But the philosophical implications are still staggering. The quantum eraser experiment is a powerful demonstration of the holistic and non-local nature of quantum reality. It shows that an entangled system is a single, indivisible whole, and that its properties cannot be understood by looking at its parts in isolation. The behavior of the signal photon is inextricably linked to the fate of its distant, entangled twin, and the reality of the system is only fully defined when we consider the entire experimental setup, including the final measurements made on both particles. It is also a profound illustration of the deep connection between information and physical reality in the quantum world. The presence or absence of which path information is not just a matter of our knowledge. It is a physical variable that has a direct and tangible effect on the behavior of the system. To erase information is not just a mental act. It is a physical act that can restore the wave-like, superpositional nature of a quantum system. The possible applications of this principle, while still largely theoretical, are tantalizing. The quantum eraser provides a powerful tool for exploring the fundamental nature of quantum measurement and decoherence, which is crucial for the development of robust quantum computers. The ability to control and manipulate quantum information, to erase it, and to restore quantum coherence could be a key ingredient in building fault-tolerant quantum memory and communication systems. But beyond any potential technological applications, the quantum eraser holds a deep and enchanting allure. It is a cosmic magic trick, a demonstration of the universe's ability to operate in ways that are far more subtle, strange, and interconnected than our classical minds could have ever conceived. It is a crack in our familiar worldview, a window into a deeper, more holistic, and more mysterious reality. A reality where the past, the present, and the future are bound together in a beautiful and paradoxical quantum dance. What if the familiar one-way street of time, the relentless march from cause to effect, is not a fundamental law of the universe, but a macroscopic illusion? What if, at the deepest level of reality, the future can ripple backwards to influence the past? This is the radical and mind-bending concept of retrocausality, an idea that is so counterintuitive that it seems to belong to the realm of fantasy, but which is being seriously considered by some physicists as a potential way to resolve some of the deepest paradoxes of quantum mechanics. At its core, retrocausality challenges our most basic and most cherished assumption about the nature of time, that causation is a one-way street. In our everyday world, events unfold in a clear, linear sequence. You drop a glass, and then it shatters. The cause precedes the effect. The idea that the shattering of the glass could somehow influence the act of dropping it is absurd. But in the strange, probabilistic world of the quantum, the rules of cause and effect are not so clear-cut. Retrocausality proposes that the relationship between events is not a simple, forward-moving chain, but a more complex, self-consistent loop, where influences can travel both forwards and backwards in time. This is not about sending messages to the past to change history. It is about a more subtle and more fundamental temporal symmetry in the laws of nature, a symmetry that is hidden from us in our macroscopic world, but which may be at play in the quantum realm. The idea of retrocausality has its roots in some of the earliest debates about the nature of quantum mechanics. It was proposed as a way to explain the spooky action at a distance of quantum entanglement without violating the principle of locality. In a retrocausal picture, when you measure one of a pair of entangled particles, you are not instantaneously influencing its distant partner. Instead, your measurement choice sends an influence back in time to the moment when the particles were first entangled, and this influence then travels forward in time with the other particle, ensuring that its measurement outcome will be correlated with yours. It is a strange and seemingly convoluted explanation, but it is one that can, in principle, reproduce all the predictions of quantum mechanics without any faster-than-light communication. More recently, retrocausality has found a new and fascinating playground in the context of the delayed choice and quantum eraser experiments. As we have seen, these experiments seem to show a future measurement choice, retroactively determining the past behavior of a particle. While these results can be explained without invoking retrocausality, by appealing to the holistic and non-local nature of the quantum state, a retrocausal interpretation offers a different, and for some, a more intuitive, way of thinking about the problem. It takes the apparent retroactivity at face value. The choice made by the experimenter in the future sends a real physical influence back in time to the double-slit barrier, telling the particle whether to behave as a wave or a particle. The past, in this picture, is not a fixed and unchangeable record. It is a pliable, dynamic entity that is constantly being shaped by its relationship with the future. It is crucial to emphasize that retrocausality, as it is currently understood, does not allow for the kinds of paradoxes that are so beloved of science fiction. You cannot send a message back in time to tell yourself the winning lottery numbers, or to warn your past self not to make a terrible mistake. The influences are thought to be at the level of the quantum wave function, shaping the probabilities of events, not determining their specific outcomes in a controllable way. The universe, in a retrocausal model, is still self-consistent. The future can influence the past, but only in a way that is consistent with the present. It is a closed, logical loop. The grandfather paradox, for example, is avoided because the universe would simply not allow for a self-contradictory history to be created. If you were to travel back in time to try and prevent your own birth, the retrocausal influences would conspire to ensure your failure. The gun would jam, the car would break down, your resolve would fail. The timeline is robust. This is a concept that is incredibly difficult to test experimentally. The influences are subtle, and they are woven into the very fabric of quantum probability. But theoretical physicists are actively working on developing new experimental protocols that could distinguish between a standard, forward causal quantum mechanics and a retrocausal one. The practical applications of retrocausality, if it is a real feature of our universe, are, at this stage, purely in the realm of speculation, but the philosophical implications are profound. It would mean that our understanding of time, of causality, of free will, and of the relationship between the past, the present, and the future would need to be fundamentally rewritten. It would suggest a universe that is not a linear, unfolding story, but a single, holistic, four-dimensional block of space-time, in which all of time exists at once, and the connections between events are not limited to a single, forward-moving direction. It would be a universe where the future is not just a passive consequence of the past, but is an active participant in its creation. The pursuit of these answers is more than just an intellectual exercise. It is a testament to the human capacity to question what once seemed unquestionable, to imagine realities that are far beyond our everyday experience. and to relentlessly probe the deepest and most fundamental mysteries of existence. Retrocausality is a bold and delicate idea, a whisper from the frontier of physics that hints at a universe that is far more strange, more interconnected, and more wondrously complex than we have ever dared to imagine. Quantum physics often feels like a puzzle that you can't quite finish. Each piece seems to promise a glimpse of a larger, coherent picture, but the edges never quite seem to align. For decades, one of the most confounding aspects of the theory has been the measurement problem, the question of what happens when we observe a quantum system, when the ghostly probabilistic world of superposition collapses into a single, definite reality. The traditional Copenhagen interpretation simply posited that this collapse happens without explaining how or why. This was a deeply unsatisfying state of affairs for many physicists. Then, in the 1950s, a young doctoral student at Princeton named Hugh Everett III came along with a proposal that was as audacious as it was elegant. He suggested that the collapse never happens. The quantum wave function, with all its superpositional possibilities, is the complete and final description of reality. And when a quantum event with multiple possible outcomes occurs, the universe itself splits into multiple parallel universes, one for each possible outcome. This is the many worlds interpretation of quantum mechanics, and it is an idea that, if true, would completely and utterly transform our understanding of reality. Imagine flipping a coin. In the many worlds view, the very act of flipping the coin does not lead to a single outcome of heads or tails. It leads to a branching of reality. A universe is created where the coin lands heads and another equally real. Universe is created where it lands tails. You, the observer, also split. One version of you sees the heads and another version sees the tails, and each version is completely unaware of the other's existence. In this picture, the entire history of the universe is a constantly branching tree of possibilities, a multiverse of parallel realities, where every quantum choice, every probabilistic event has led to the creation of a new world. The implications of this theory are breathtaking, and for many, deeply unsettling. It means that for every decision you have ever made, there is another version of you in a parallel universe who made the opposite choice. There is a universe where you took that job you turned down, a universe where you married your high school sweetheart, a universe where you caught that train you missed. Somewhere out there, in the vast branching landscape of the multiverse, all of your unlived lives are being lived out by other, equally real versions of yourself. It is an idea that is both exhilarating and dizzying, one that challenges our most basic assumptions about our own uniqueness and the nature of our own personal history. But how does this strange and wonderful idea of a branching parallel reality change our understanding of an even stranger concept? Time travel. The many worlds interpretation offers a beautiful and elegant solution to one of the most famous and intractable paradoxes of time travel. The grandfather paradox. The paradox, in its classic form, goes like this: if you were to build a time machine, travel back to the past, and prevent your own grandfather from meeting your grandmother, then your parent would never be born, and therefore you would never be born. But if you were never born, how could you have traveled back in time to commit the act in the first place? It is a logical contradiction that seems to make any form of time travel that can alter the past a physical impossibility. But in the many worlds interpretation, this paradox simply dissolves. When you travel back in time, you are not traveling into the past of your own specific branch of the multiverse. You are, in effect, crossing over into a different branch. When you interfere with the past in this new branch by, for example, preventing your grandfather from meeting your grandmother, you are not changing your own history. You are simply creating a new timeline, a new branch of the multiverse, one in which you were never born. But your original universe, The one from which you departed remains completely unchanged. The version of you that built the time machine still exists, still has a grandfather, and still has a history. You have not erased yourself from existence. You have simply become a visitor, an orphan of time, in a parallel reality. The grandfather paradox is resolved because the cause and the effect are now in two separate, non-communicating universes. This makes time travel, at least in a theoretical sense, a much less dangerous and more self-consistent proposition. It is not an act of rewriting a single sacred timeline, but an act of exploring the vast, pre-existing landscape of parallel realities. It is less like editing a document and more like choosing to read a different book. But the many worlds interpretation, for all its elegance, does not come without its own set of challenges and complexities. For one, can we still call it time travel if you can never return to your original timeline? If every trip to the past is a one-way ticket to a new, alternate reality, then the very concept of returning to your own time becomes meaningless. And how would you navigate this infinite, branching tree of possibilities? If you wanted to travel to a specific past event, how would you pinpoint the exact branch of the multiverse you wanted to visit? The sheer, incomprehensible vastness of the possibilities, while exciting, also makes the idea of a controlled, targeted form of time travel seem dauntingly, if not infinitely, complex. And of course, the biggest challenge of all is the fact that the many worlds interpretation, like the broader concept of the multiverse, is at present unfalsifiable. We have no way to experimentally verify the existence of these other parallel universes. They remain, for now, beautiful and compelling mathematical constructs, born from the strange logic of quantum mechanics, but not yet a part of our confirmed empirical reality. And yet, the many worlds interpretation continues to be a popular and influential idea among many theoretical physicists. It is a testament to the profound and often uncomfortable places that our science can lead us. It is an invitation to confront the very limits of our own understanding, to reconsider everything we think we know about the nature of time, of choice, of identity, and of existence itself. It is a mind-expanding lens through which to view the universe, a lens that reveals a reality that is not a single, linear story, but an infinite, branching, and wondrously complex tapestry of all possible stories. And it is a reminder that, in the strange and beautiful world of quantum physics, the line between science and science fiction is often a very thin and very blurry one indeed. Imagine a world where time is not a linear, unyielding arrow, where the future does not just follow the past, but can loop back to influence it, where the very boundaries of causality blur into a surreal and beautiful dance. This is not the opening to a fantastical novel, but the foundation of a real and mind-bending concept in theoretical physics, the closed timelike curve, rooted in the elegant but often strange equations of Einstein's general theory of relativity. These theoretical pathways propose that the fabric of space-time may not be a simple, flat sheet, but can, under certain extreme conditions, bend and fold back on itself, creating loops in time. While the idea has its foundations in the classical, deterministic world of Einstein, its profound and paradoxical implications find their most fascinating expression when they intersect with the strange, probabilistic rules of the quantum realm. Today, we will explore this fascinating intersection, focusing on the scientifically grounded theories that are pushing the boundaries of our understanding of time, and offering us a tour through a universe that is far stranger and more compelling than any science fiction script. Closed timelike curves, or CTCs, first emerged as a possibility from certain exact solutions to Einstein's field equations. These equations describe how the presence of mass and energy curves the geometry of space-time. In most familiar situations, this curvature is gentle, leading to the familiar, forward-moving flow of time. But in some exotic and highly theoretical scenarios, the curvature can become so extreme that it creates pathways that loop back into their own past. Imagine tracing a path through the 4 dimensions of space-time that brings you back to your starting point, not just in space, but in time as well. This is a closed, timelike curve. One of the first and most famous of these solutions was discovered by the brilliant logician and mathematician Kurt Gödel in 1949. He found that in a universe that is rotating as a whole, it would be possible for a sufficiently fast-moving spaceship to travel on a path that would return it to its own past. Later, the physicist Frank Tipler explored the theoretical construct of a Tipler cylinder, an infinitely long and incredibly dense rotating cylinder, which could also, in theory, generate CTCs around it. These models, while mathematically sound, are thrilling for the imagination, but they also raise profound questions about whether nature would ever allow such structures to form. They require conditions a rotating universe, an infinite cylinder that do not seem to correspond to the cosmos we observe. But beyond their theoretical elegance, closed, time-like curves force us to confront the great paradoxes of time travel. If such a pathway through time exists, could an object or a person journey into their own past? This possibility immediately opens the door to the grandfather paradox, a time traveler who goes back and interferes with the past in a way that prevents their own existence. For example, by preventing their grandparents from ever meeting, creates a logical contradiction that seems to make such a journey impossible. For a long time, this was seen as a powerful argument against the physical possibility of time travel. And yet, the mathematics of general relativity does not explicitly forbid the existence of CTCs. This has left physicists to grapple with a deep and perplexing question: do these paradoxes represent a fundamental flaw in our understanding of time? Or is there a deeper, and perhaps quantum principle at play that resolves them? The creation of a closed time-like curve, even in theory, is not a simple matter. The mathematical models that allow for them typically require the existence of exotic matter, a hypothetical form of matter with a negative energy density. This is a substance that would have bizarre anti-gravitational properties. And it is something that has never been observed in nature, while some subtle quantum phenomena, like the Casimir effect, can create localized regions of negative energy. The existence of a macroscopic, stable form of exotic matter remains highly speculative and may be forbidden by the fundamental laws of physics. The energy requirements to warp space-time into a loop are also astronomically high, far beyond anything our current, or even foreseeable, technology could ever achieve. But this is where the strange and beautiful world of quantum mechanics offers a new and intriguing avenue of exploration. Unlike the deterministic framework of classical physics, where an object has a single, definite history, the quantum world is a realm of probabilities and uncertainties. This has led some physicists to propose that the paradoxes of time travel might be resolved, not by forbidding CTCs, but by applying the rules of quantum mechanics to them. This is the idea of quantum self-consistency. In a quantum model of a CTC, a particle traveling on a time loop does not have a single, classical trajectory. It has a wave function, a superposition of all possible histories. The principle of self-consistency, most famously formulated by the physicist David Deutsch, proposes that the only histories that are allowed are those that are self-consistent. The particle can interact with its own past, but only in a way that does not create a logical contradiction. For example, in a quantum version of the grandfather paradox, a particle sent back in time to flip a switch that would prevent its own creation would not have a definite outcome. It would exist in a superposition of states, and the probabilities of the different outcomes would adjust themselves in such a way that no paradox is created. The probability of the particle successfully flipping the switch would be exactly balanced by the probability of it failing, leading to a self-consistent, if probabilistic, solution. This is an elegant and deeply quantum way of resolving the paradoxes. It suggests that the universe has a built-in, probabilistic censorship mechanism that prevents logical contradictions from ever occurring. Researchers have even begun to test these ideas using quantum computers to simulate the behavior of a qubit traveling on a closed timelike curve. These simulations have confirmed the predictions of Deutsch's model, showing that a self-consistent solution can always be found without any need to invoke a paradox. What's even more fascinating is that these simulations have shown that a qubit interacting with its past self through a CTC can gain extraordinary computational power, allowing it to solve certain problems that are thought to be intractable for even a standard quantum computer. This has led to the speculative, but tantalizing, idea that nature might be using the logic of closed timelike curves at some deep, hidden level of reality. As captivating as these ideas are, it is crucial to remember the immense challenges that lie ahead. To date, there is no experimental evidence for the existence of closed timelike curve. The exotic solutions of general relativity that contain them remain mathematical curiosities, tied to highly specific and often physically unrealistic conditions. Our technological capacity to manipulate space-time, which would require the harnessing of exotic matter or the generation of cosmic-scale energies, is nowhere near what would be needed to create a time loop in the laboratory. And even within the realm of quantum mechanics, while the simulations are intriguing, the practical implementation of a system that could genuinely send a particle on a journey into its own past remains light years away. These considerations underline a humbling truth about our current understanding. We are like children, just beginning to learn the alphabet of a deep and complex cosmic language. But in the gaps of our knowledge, in the tension between the classical and the quantum, lies the source of our greatest inspiration. The study of closed timelike curves is more than just an ambitious quest to build a time machine. It is a powerful intellectual tool that forces us to rethink the fundamental laws that govern space, time, and causality. It compels us to confront the deep and unresolved conflict between the deterministic, geometric world of Einstein and the probabilistic, superpositional world of the quantum, and in doing so, it is pushing the boundaries of human knowledge, unlocking profound new insights into the very nature of reality itself. Whether through the refinement of our theories of general relativity, the advancement of quantum computation, or the revolutionizing of our cosmological models, the research into closed timelike curves is creating ripples that are felt across multiple disciplines, shaping the trajectory of scientific discovery for generations to come. Each new exploration, each new thought experiment, brings us a little closer to answering the foundational questions that have defined the human quest for understanding for millennia. And it is a bold and beautiful reminder of the audacity, the creativity, and the enduring wonder that lies at the very heart of the scientific exploration of the cosmos. The dream of time travel, of breaking free from the linear confines of our own existence, has been a powerful and persistent theme in human culture for centuries. But could this dream ever move from the realm of fiction into the world of scientific fact? While the idea of building a macroscopic time machine remains firmly in the realm of speculation, some of the most advanced and mind-bending theories in modern physics are beginning to provide a theoretical and perhaps even a quantum blueprint for how such a feat might one day be possible. The journey begins with the strange and beautiful geometry of space-time, as described by Einstein's theory of general relativity. As we have seen, this theory allows for the theoretical possibility of wormholes, or Einstein-Rosen bridges, hypothetical tunnels through the fabric of space-time that could connect two very distant locations, or even two different moments in time. The problem is that these cosmic shortcuts are predicted to be incredibly unstable, collapsing in on themselves almost instantly. To keep a wormhole open long enough for something or someone to pass through would require a form of exotic matter, a substance with a negative energy density that could prop open the throat of the wormhole, counteracting the immense gravitational forces that are trying to crush it. For a long time, this was seen as a fatal flaw in the idea of traversable wormholes. But the quantum world, with its strange and counterintuitive rules, may offer a solution. At the heart of quantum mechanics lies the concept of quantum fluctuations, the incessant energetic ripples that occur even in a perfect vacuum. These fluctuations, a direct consequence of the uncertainty principle, can give rise to localized regions of negative energy. The Casimir effect is a direct, experimental demonstration of this phenomenon. While the amount of negative energy produced in the Casimir effect is tiny, it proves that the concept is not just a mathematical fantasy. The challenge, then, is to find a way to generate and control a sufficient amount of this quantum negative energy to stabilize a macroscopic wormhole. This is a technological hurdle of almost unimaginable proportions, but it is one that has shifted the problem from a matter of fundamental physical impossibility to a matter of extreme, but perhaps not insurmountable, engineering. This is where the power of quantum computing may one day come into play. Quantum computers, with their ability to simulate complex quantum systems, are becoming an essential tool for exploring the strange and wonderful world of quantum gravity. They allow researchers to model the curvature of space-time, the behavior of quantum fields in extreme gravitational environments, and the very nature of the quantum vacuum itself. As these machines become more powerful, they may allow us to test our theories of wormhole stability and to explore the properties of exotic matter in a virtual computational laboratory. This could lay the theoretical groundwork for understanding how to manipulate spacetime in a controlled and predictable way. Another, even more speculative, but equally fascinating, quantum phenomenon that could have implications for time travel is the time crystal. A regular crystal, like a diamond or a snowflake, is a structure whose atoms are arranged in a repeating pattern in space. A time crystal, a concept first proposed by the Nobel laureate Frank Wilczek in 2012, is a structure whose lowest energy state is one in which the constituent particles are in a periodic, repeating motion. It is a system that spontaneously breaks time translation symmetry. In a sense, it has a built-in perpetual clock. What is truly remarkable is that this perpetual motion does not require any input of energy and does not violate the laws of thermodynamics, as it occurs in the system's ground state. The existence of time crystals was experimentally confirmed in 2016, a stunning demonstration of a new and exotic state of matter. The practical applications of time crystals are still being explored, but they could have profound implications for quantum computing, for high-precision timekeeping, and perhaps even for our understanding of the nature of time itself. Could a time crystal, with its stable, repeating temporal loop, be used to anchor or stabilize a closed timelike curve? Could it be used to create a localized region of spacetime where the normal linear flow of time is disrupted? These are ideas that are on the very edge of theoretical physics, but they are a beautiful example of how the discovery of new, exotic quantum phenomena can open up entirely new avenues of thought. Finally, the strange, non-local connection of quantum entanglement may offer yet another, and perhaps the most profound, pathway to rethinking our relationship with time. The EREPR conjecture, a bold and beautiful idea proposed by physicists Leonard Susskind and Juan Maldatina, suggests a deep and unexpected equivalence between two of the strangest concepts in modern physics, quantum entanglement and wormholes. The conjecture posits that every pair of entangled particles is, in some deep, geometrical sense, connected by a microscopic wormhole. This is a mind-bending idea, one that suggests that the strange, non-local connection of entanglement is not a spooky, disembodied action at a distance, but has a real, physical, and geometrical manifestation in the structure of space-time itself. It suggests a deep unity between the laws of quantum mechanics and the laws of general relativity. A hint that these two great theories are just two different descriptions of the same underlying reality. Does this mean we can use entanglement to travel through wormholes? Not in any simple sense. The wormholes in the EREPR conjecture are thought to be non-traversable. But the idea that the very fabric of space-time is woven from the threads of quantum entanglement is a revolutionary one. It suggests that if we could learn to manipulate and control large-scale, multi-particle entanglement, we might, in effect, be learning to manipulate and control the geometry of space-time itself. This is the ultimate, and perhaps the most ambitious frontier in the quest for a quantum time machine. It is a quest that is no longer just about building bigger spaceships or finding cosmic shortcuts. It is about understanding and harnessing the deepest, most fundamental, and most mysterious properties of the quantum world itself. It is a journey that will require leaps of imagination, of experimental ingenuity, and of theoretical brilliance. And it is a journey that, whether it ultimately succeeds in building a time machine or not, is already transforming our understanding of the universe, and our own strange and wonderful place within it. The dream of traveling through time, of breaking the chains of the linear present, has long been a powerful and enduring part of the human imagination. But could this dream ever be more than just a dream? Could the strange and beautiful laws of quantum mechanics provide a key to unlocking the mysteries of time itself? The phenomenon of quantum entanglement, the spooky action at a distance that so perplexed Einstein, lies at the very heart of this inquiry. Entanglement describes a profound and mysterious connection between two or more particles, a bond so deep that their fates remain intertwined. No matter how far apart they are separated in space, a measurement on one particle instantly influences the state of the other. For a long time, this was seen as a bizarre, but ultimately limited, feature of the quantum world, a strange correlation that could not be used to send information faster than light. But in recent years, a new and radical idea has emerged, one that suggests that this spooky connection may have a deep and unexpected relationship with the very geometry of space-time. This is the EREPR conjecture, a bold and beautiful hypothesis that proposes a fundamental equivalence between quantum entanglement and wormholes. It is an idea that suggests that every pair of entangled particles is connected by a tiny, microscopic wormhole, a shortcut through the fabric of space-time. This is not to say that we can simply entangle two particles and then crawl through the wormhole that connects them. The wormholes in the EREPR conjecture are thought to be non-traversable. They are more like a private, quantum information channel than a physical tunnel. But the conjecture itself is revolutionary. It suggests that the strange, non-local connectivity of the quantum world and the dynamic geometric structure of the relativistic world are not two separate things, but are two different descriptions of the same underlying reality. The very fabric of space-time in this picture may be woven from the threads of quantum entanglement. The universe is not a classical, geometric stage upon which a quantum drama plays out. The stage and the actors are one and the same. This has profound implications for our understanding of time. If the geometry of space-time is emergent from the quantum state of the universe, then time itself may be an emergent phenomenon, a property that arises from the complex web of entanglements that connect all the particles in the cosmos. This could provide a new way to think about the arrow of time, the forward flow of time. The increase of entropy may be related to the increasing complexity of the entanglement structure of the universe as it evolves. And it opens up the tantalizing, if highly speculative, possibility that by manipulating entanglement, we could, in a sense, be manipulating the structure of time itself. The EERE-EPR conjecture is still a theoretical idea, one that is on the cutting edge of research in quantum gravity. But the connection between entanglement and space-time is not just a matter of abstract theory. It is being probed in real and increasingly sophisticated laboratory experiments using quantum processors, the powerful new machines that can control and manipulate the quantum states of individual particles. Scientists are now able to simulate the behavior of quantum systems in curved space-time, and even to create laboratory analogs of wormholes and black holes. In one groundbreaking experiment, researchers at Google, in collaboration with physicists at Caltech, used their Sycamore quantum processor to create a simulation of a traversable wormhole. They did this by creating a highly entangled state between two sets of qubits on their chip and then sending a quantum signal from one set to the other. They found that the signal propagated in a way that was consistent with the signal having traveled through a wormhole in a holographic toy model of a universe. This was not a real wormhole in physical space. Of course, it was a simulation, a quantum computation, but it was a stunning demonstration of the deep connection between the mathematics of quantum entanglement and the physics of space-time geometry. It was the first experimental realization of the idea that the dynamics of a gravitational system can be emergent from the quantum information processing of a non-gravitational one. These are early days, and the technological challenges are immense. Creating and maintaining the large-scale, highly entangled quantum states needed to test these ideas with precision is a colossal experimental hurdle. The fragility of quantum coherence, its susceptibility to decoherence from the surrounding environment, is a constant battle for quantum engineers. But the progress is rapid. And as our quantum technologies become more powerful, as we learn to control and manipulate the strange and beautiful world of entanglement with ever greater precision, we will be able to probe these deep connections between the quantum and the cosmos in new and profound ways. The potential implications are too enticing to ignore. If the link between entanglement and space-time is a real physical feature of our universe, could we one day learn to harness it? Could we create and stabilize a macroscopic, traversable wormhole by creating a specific, highly entangled state of matter and energy? Could we use the non-local connections of entanglement to create shortcuts, not just through space, but through time? These are questions that are on the very edge of our current scientific understanding. They are questions that may not be answered in our lifetimes. But they are questions that are no longer confined to the realm of science fiction. They are being asked and explored in the laboratories and on the blackboards of some of the world's leading physicists. The quest to understand the link between quantum entanglement and space-time is one of the most exciting and ambitious frontiers in all of science. It is a quest that promises to unify our two great theories of the universe, and in doing so, to reveal a reality that is far deeper, more mysterious, and more wondrously interconnected than we have ever dared to imagine. The idea of traveling backwards in time, of revisiting the past, is a concept that is fraught with paradox. The infamous grandfather paradox, in which a time traveler alters the past in a way that prevents their own existence, has long been seen as a fundamental, logical barrier to any form of time travel that can change history. But the strange, probabilistic nature of the quantum world may offer a way out, a way to have time travel without the paradoxes. This is a concept that is now being explored, not just in thought experiments, but in real laboratory simulations using some of the most advanced quantum computers in the world. Imagine a particle, a single qubit, traveling on a closed timelike curve, a path through space-time that loops back into its own past. In a classical world, this would be a recipe for paradox. If the particle is sent back in time to flip a switch that prevents it from ever being sent, we have a logical contradiction. But in the quantum world, the particle is not a classical object with a definite state. It is a wave function, a superposition of all its possible states. And according to the self-consistency principle proposed by David Deutsch, the only histories that are allowed on a CTC are those that are self-consistent. The universe, in a sense, edits out the paradoxes. Quantum simulations of this process, carried out by teams at IBM and Google using their powerful quantum processors, have shown how this can work in practice. They have successfully modeled the behavior of a qubit navigating a simulated CTC, and they have found that the quantum system naturally avoids paradox. The probabilities of the different outcomes of the qubit's interaction with its past self adjust themselves in such a way that no logical contradiction is ever created. It is as if the universe has a built-in probabilistic censorship mechanism. This is a stunning result. It suggests that time travel into the past may not be as logically impossible as we once thought. The quantum world, with its inherent fuzziness and its superposition of possibilities, seems to have a natural resilience to the paradoxes that would plague a classical time traveler. These experiments have also revealed something else that is equally profound, the concept of retrocausality. In these simulations, the state of the particle seems to be influenced by the measurement that will be made on it in the future. The choices of the experimenter seem to ripple backwards in time to shape the behavior of the particle in the past. This is not to say that information is being sent back in time in a controllable way. The outcome of any single measurement is still random, but the statistical correlations between the measurements show a clear and deeply strange retrocausal pattern. The future, in some subtle quantum mechanical way, seems to be reaching back to co-create the past. These advances in our ability to simulate the strange temporal dynamics of the quantum world are turning what was once pure speculation into a field of active experimental research. The notion of retrocausality, the idea that effects can precede their causes, is no longer just a philosophical curiosity. It is a concept that is being tested and explored in controlled laboratory settings. These simulations are showing that a retrocausal quantum mechanics can be fully self-consistent. The particles in these models seem to anticipate the future measurements that will be made on them, but they do so in a way that never violates the overall integrity and logical consistency of the system. This elegant, self-organizing property of quantum systems is a testament to the deep and often hidden logic that governs the universe at its most fundamental level. The role of quantum entanglement in these scenarios is crucial. When particles are entangled, their fates are linked, no matter how far apart they are in space or, perhaps, in time. This non-local connection may be the key to enforcing the self-consistency of the universe. It is as if the entangled particles are in constant, instantaneous communication, negotiating their shared reality to ensure that no paradoxes are ever created. This interconnectedness raises deep questions about the very nature of time itself. Is time an emergent property, something that arises from the deeper, more fundamental reality of the quantum state of the universe? In our everyday macroscopic world, time appears to be a linear, forward-moving arrow. But this may just be a consequence of the scale at which we operate, a statistical effect that emerges from the countless random interactions of the quantum world. At the fundamental quantum level, the distinction between past, present, and future may be far more blurry, more interconnected, and more dynamic than we can ever directly perceive. The interface between quantum computing and these deep theoretical questions is creating a new and exciting era of exploration. Companies like IBM and Google are not just building more powerful computers, they are building laboratories for probing the very foundations of reality. Their quantum processors, with their ability to handle the immense complexity of quantum simulations, are allowing researchers to explore the strange temporal landscapes of closed timelike curves and retrocausality in a way that was previously unimaginable. These simulations are exposing the limitations of our classical, intuitive understanding of time and causality. They are forcing us to confront a reality that is probabilistic, non-local, and perhaps even temporally symmetric. And in doing so, they may be providing us with the first tentative clues to a new and more unified understanding of the universe. A theory of quantum gravity that can finally reconcile the two great pillars of modern physics. The exploration of quantum time travel is more than just a quest to build a fantastical machine. It is a journey into the very heart of the quantum mystery. A journey that is challenging our deepest assumptions, expanding our intellectual horizons, and revealing a universe that is far more strange, more beautiful, and more wondrously interconnected than we have ever dared to dream. The universe has always fascinated humanity. A vast and silent tapestry woven with unanswered mysteries. Yet, beyond the familiar cosmos of stars and galaxies, there may be more. Hidden dimensions, parallel realities, and entire worlds could exist just beyond the veil of our perception. The laws of physics as we know them might only be a local chapter in a much grander, more complex cosmic story. A design that stretches far beyond the confines of a single universe. It is this tantalizing possibility, this deep and enduring quest to understand the ultimate nature of reality, that has led humanity to build one of the most powerful and ambitious machines ever created, the Large Hadron Collider. This is not just an instrument of science. It is a time machine, a reality probe, a technological marvel designed to recreate the fiery, primordial conditions of the Big Bang and to unlock the deepest secrets of existence itself. Today, we embark on a journey into the heart of this scientific cathedral, an exploration that will take us from the colossal 27-kilometer ring buried deep beneath the Swiss-French border to the strange and beautiful realm of quantum collisions, where new and exotic forms of reality are forged for a fleeting, infinitesimal moment. We will explore the mind-bending concept of extra dimensions, the mysterious gravitational whispers of dark matter, and the ultimate philosophical challenge of a potential multiverse. Following the trail of the brilliant physicists and theorists who have dedicated their lives to this quest, we will examine the incredible discoveries that have already been made, and the profound, and often unsettling, questions that still haunt the frontiers of our knowledge. Could our reality be just one of a vast and perhaps infinite number of other realities? Are there other parallel versions of ourselves, living out the consequences of every choice we never made? And will the Large Hadron Collider, in its relentless and powerful probing of the subatomic world, finally provide us with the first tantalizing hints of an answer? The search for the ultimate truth has begun, and it is a search that is taking place not in the distant heavens, but in the deep, dark, and wonderfully mysterious heart of matter itself. The Large Hadron Collider, or LHC, stands as a monument to human curiosity and collaboration. Nestled at CERN, the European Organization for Nuclear Research, and straddling the border between Switzerland and France, this immense machine is a 27-kilometer-long underground circular tunnel, a racetrack for the very building blocks of our universe. Its purpose is both elegantly simple and profoundly ambitious: to accelerate subatomic particles, like protons, to speeds just shy of the speed of light, and then to smash them together with an energy that has not been seen in the cosmos since the first fiery moments after the Big Bang. In the subatomic debris of these cataclysmic collisions, scientists search for the ghostly signatures of new particles, new forces, and new symmetries of nature, seeking clues to the deepest mysteries of our existence. The LHC is the culmination of a long scientific lineage, the latest and most powerful in a series of particle accelerators that have, over the last century, peeled back the layers of reality, revealing an ever deeper and ever stranger subatomic world. But the LHC was designed with a specific set of profound and long-standing questions in mind, questions that had brought the field of particle physics to a critical juncture. Physicists were grappling with the origin of mass. Why do some fundamental particles possess it, while others do not? They were hunting for the identity of dark matter, the invisible substance that makes up the vast majority of the matter in the universe, and they were trying to understand the deep and seemingly miraculous asymmetry between matter and antimatter, the reason our universe is made of stuff at all. The standard model of particle physics, the remarkably successful theory that describes all the known fundamental particles and their interactions, provides a beautiful and coherent framework for our understanding of the subatomic world. But it is an incomplete story. It has glaring omissions. It does not include the force of gravity. It has no explanation for dark matter or dark energy. It cannot account for the matter-antimatter imbalance. The LHC was conceived as a standard model-breaking machine, a powerful tool designed to find the cracks in our current understanding, the subtle anomalies that would point the way to a new, deeper, and more comprehensive theory of reality. The dream of a collider powerful enough to recreate the conditions of the early universe had been cherished by physicists for decades, but the technological hurdles were immense. It required the development of some of the most powerful superconducting magnets ever built, capable of generating magnetic fields thousands of times stronger than the Earth's, to bend the high-energy proton beams around the 27-kilometer ring. It required an ultra-high vacuum, emptier than interplanetary space, to ensure the proton beams could travel unimpeded on their journey. And it required the construction of some of the largest and most complex scientific instruments ever conceived, the massive cathedral-sized detectors like ATLAS and CMS that are designed to capture and to analyze the fleeting subatomic shrapnel of the particle collisions. After years of meticulous planning and a truly global collaborative construction effort involving thousands of scientists and engineers from over 100 countries, the LHC was finally completed and switched on in 2008. At its core, the science of the LHC is a form of cosmic archaeology. By smashing protons together with incredible energy, physicists are, for a fleeting, infinitesimal moment, recreating the hot, dense, and energetic conditions of the primordial universe. In that fraction of a second, new and exotic particles, some of which have not existed in nature since the Big Bang, can be forged from the pure energy of the collision, as described by Einstein's famous equation, E equals mc squared. Many of these particles are incredibly unstable, decaying into more familiar particles in a fraction of a second. The job of the giant detectors is to act as a kind of high-tech, three-dimensional digital camera, to track the paths, the energies, and the identities of the hundreds of particles that fly out from each collision, and to reconstruct the story of what happened in that moment of creation. It is a process of sifting through a mind-boggling amount of data, trillions of collisions every second, to search for the rare, telltale signature of a new particle, a new force, a new discovery. It is a search for a needle in a cosmic haystack, a search that is pushing the limits of our technology, our computational power, and our very understanding of the fundamental nature of reality. The immense energy of the particle collisions at the LHC is the key to its scientific power. In the world of particle physics, higher energy translates directly to the ability to probe smaller distances and to create heavier, more exotic particles. The journey of a proton at the LHC is a journey of almost unimaginable acceleration. It begins in a simple bottle of hydrogen gas. The hydrogen atoms are ionized, stripped of their single electron, leaving bare protons. These protons are then injected into a series of smaller pre-accelerator rings, where they are given a kick of energy by powerful oscillating electric fields in radio frequency cavities. With each kick, they move faster, and their path is guided and focused by a complex array of magnets. As they gain speed, they are passed from one accelerator to the next, like runners in a relay race, until they are finally injected into the main 27-kilometer ring. Here, they will circle for hours, making over 11,000 laps every single second, their energy boosted with each turn by the powerful superconducting radio frequency cavities. The protons travel in two counter-rotating beams, each beam containing trillions of protons, all traveling at an incredible 99.999991% of the speed of light. At this extreme relativistic speed, each proton has the kinetic energy of a flying mosquito, a seemingly tiny amount of energy, but an immense amount when concentrated into a single subatomic particle. At 4 specific points around the ring, these two hair-thin beams of high-energy protons are focused down to an even smaller size and are made to cross through each other. This is where the scientific magic happens. In the vast majority of cases, the protons in the two beams will simply pass by each other without interacting. But occasionally, two protons will collide head-on, releasing their immense, concentrated energy in a tiny subatomic fireball, a miniature Big Bang. It is in this fireball, for a fleeting, infinitesimal moment, that the conditions of the early universe are recreated. The raw energy of the collision is converted into a shower of new particles, a fleeting glimpse of the exotic zoo of particles that populated the cosmos in its first moments. And surrounding these collision points are the giant general-purpose detectors, ATLAS and CMS. These are marvels of modern engineering, multi-story structures packed with layers of different kinds of sensors, each designed to detect a different type of particle. The inner layers, closest to the collision, are silicon pixel and strip detectors designed to track the paths of charged particles with incredible precision. Surrounding these are the calorimeters, which are designed to measure the energy of the particles by absorbing them. And on the outermost layers are the muon chambers, which are designed to detect muons, a heavier cousin of the electron, which are one of the few particles that can punch through all the inner layers of the detector. The amount of data generated by these detectors is staggering. Each collision can produce thousands of particles, and there are billions of collisions happening every second. It is a torrent of information that is far beyond the capacity of any human to analyze. And so, a complex, multi-layered trigger system is used to filter the data in real time, selecting only the most interesting and potentially significant events to be saved for later analysis. This is a process that relies on sophisticated and increasingly AI-driven algorithms to search for the specific telltale signatures of new physics. The reason the LHC requires such high energies is not just to create new particles, but also to test the predictions of our current theories in a new and unexplored regime. The standard model of particle physics has been remarkably successful, but it is an incomplete theory. By pushing to higher and higher energies, physicists are hoping to find the limits of the standard model, to find a place where its predictions break down, a place that will point the way to a new, more fundamental theory of reality. The LHC is not just a machine for discovering new particles. It is a machine for discovering new questions, for pushing the boundaries of our knowledge, and for revealing the deep and often hidden structure of the universe itself. One of the most profound and long-sought answers that the LHC was built to provide was the confirmation of the existence of the Higgs boson. This elusive particle, first theorized in the 1960s by a group of physicists including Peter Higgs, was the missing cornerstone of the standard model of particle physics. It was the key to understanding one of the most fundamental and yet most mysterious properties of our universe: the origin of mass. The standard model, in its original and most elegant form, predicted that all the fundamental particles should be massless. But this is clearly not the case. We know that electrons, quarks, and the W and Z bosons all have mass. The Higgs mechanism was the brilliant theoretical solution to this puzzle. It proposed the existence of a new invisible energy field that permeates all of space, now known as the Higgs field. In the very early hot universe, this field was off and all the particles were massless. But as the universe cooled, the Higgs field underwent a phase transition and turned on, acquiring a non-zero value everywhere in the vacuum. And it is the interaction of the other fundamental particles with this background Higgs field that gives them their mass. Imagine moving through a thick, viscous liquid like molasses. A particle that interacts strongly with the Higgs field is like a person trying to wade through this molasses. It experiences a drag, an inertia, which we perceive as mass. A particle that interacts weakly with the field experiences less drag and has a smaller mass. And a particle that does not interact with the field at all, like the photon, experiences no drag and remains massless. The Higgs boson is the quantum particle associated with this field. It is a localized, vibrating excitation of the Higgs field itself, a ripple in the cosmic molasses. The standard model made a precise prediction for the properties of the Higgs boson, but it did not predict its mass. Finding the Higgs and measuring its mass was one of the primary goals of the LHC. The task was not an easy one. The Higgs boson is incredibly unstable, decaying into other, more familiar particles in an almost instantaneous fraction of a second. It is also incredibly rare, produced in only about 1 in every 10 billion proton-proton collisions at the LHC. The challenge for the experimentalists was to sift through the immense, chaotic debris of the collisions and to find the tiny, statistical excess of events that would signal the fleeting existence of the Higgs. It was a search that required the analysis of a truly astronomical amount of data, a task that pushed the limits of modern computing and statistical analysis. And then, on the 4th of July, 2012, in a historic and emotional announcement at CERN, the ATLAS and CMS collaborations jointly announced that they had, independently, discovered a new particle with a mass of about 125 gigaelectronvolts, a particle whose properties were consistent with those of the long-sought Higgs boson. It was a moment of profound triumph for science, a confirmation of a 50-year-old theoretical prediction, and the culmination of one of the greatest and most ambitious scientific endeavors in human history. The discovery of the Higgs boson was a monumental achievement. It confirmed the existence of the Higgs field and provided the missing piece of the standard model puzzle. It gave us a deep and experimentally verified understanding of the origin of mass, one of the most fundamental properties of our reality. But in science, every answer seems to give rise to new and often deeper questions. And the discovery of the Higgs boson was no exception. While the particle's existence confirmed the general picture of the Higgs mechanism, its specific, measured properties have raised a host of new puzzles and have pointed the way towards a new and largely unexplored frontier of physics. For example, why is the mass of the Higgs boson so light? Quantum mechanics predicts that the Higgs mass should receive huge quantum corrections from its interaction with the virtual particles of the vacuum, which should drive its mass up to the Planck scale, the fundamental scale of quantum gravity, which is about 16 orders of magnitude heavier than what we observe. This hierarchy problem suggests that there must be some new physics, some new symmetry of nature, like supersymmetry. That is protecting the Higgs mass from these huge quantum corrections, but so far, the LHC has found no evidence for this new physics. Another profound mystery is the nature of the Higgs field's potential energy. The shape of this potential is what determines the stability of our universe's vacuum and the measured mass of the Higgs boson. When combined with the mass of the heaviest known particle, the top quark, suggests that our universe may not be in a truly stable, lowest energy state. It may be in a metastable, or false vacuum state, a state that is stable for now, but could one day, through a process of quantum tunneling, decay into a new, true vacuum state, an event that would rewrite the laws of physics and annihilate our entire cosmos in an instant. The Higgs boson, the very particle that gives our universe its substance, may also be the harbinger of its ultimate doom. Since 2012, the research at the LHC has shifted from a search for the Higgs to a detailed, precision study of its properties. By measuring its interactions with all the other known particles, and by searching for its potential interactions with new, as yet undiscovered, particles, physicists are hoping to use the Higgs boson as a portal, a window into the new physics that we know must lie beyond the standard model. The Higgs is not the end of the story. It is the beginning of a new chapter, a chapter that may lead us to a deeper understanding of dark matter, of quantum gravity, and of the ultimate fate of our universe. Despite the monumental success of the Standard Model and the triumphant discovery of the Higgs boson, the universe continues to present us with a host of deep and profound mysteries that lie beyond the reach of our current theories. The LHC, while confirming the last piece of the Standard Model puzzle, has, so far, failed to find any direct evidence for the new physics that we know must be there. This has led to a period of deep reflection and also of great excitement. In the world of particle physics, we are standing at a crossroads, a moment where the old, familiar map of reality has run out, and we are venturing into a truly uncharted territory. One of the most glaring and most humbling of these unsolved mysteries is the nature of dark matter. Our observations of the cosmos, from the rotation speeds of galaxies to the gravitational lensing of distant light, have provided overwhelming and incontrovertible evidence that the visible matter of our universe, the stars, the gas, the dust, is just the tip of a vast cosmic iceberg. About 85% of the matter in the universe is made of a mysterious, invisible substance that does not interact with light. It is dark. We know it is there because we can feel its gravitational pull, but we have no idea what it is. The Standard Model of particle physics has no place for dark matter. None of the known particles have the right properties to be the dark matter. This means that the vast majority of the matter in the universe is made of something new, something completely outside of our current and otherwise incredibly successful theory of reality. For decades, the leading candidate for the dark matter particle was the weakly interacting massive particle, or WIMP. This was a hypothetical particle, predicted by theories like supersymmetry, that would be heavy and would interact only through the weak nuclear force and gravity. This was an attractive idea, because a WIMP with the right mass and interaction strength would have been produced in just the right abundance in the early universe to account for the observed amount of dark matter today. This WIMP miracle, as it was called, made it the focus of an intense and multi-pronged experimental search. But after decades of searching in deep underground laboratories with satellite-based telescopes and at the Large Hadron Collider, we have found no definitive evidence for WIMPs. The parameter space for the simplest and most natural WIMP models has been almost completely ruled out. This has led to a WIMPless era in particle physics, a time of great creativity and of a renewed search for alternative dark matter candidates. Perhaps dark matter is made of actions, a hypothetical ultralight particle that was originally proposed to solve a different puzzle in the theory of the strong nuclear force. Or perhaps it is made of sterile neutrinos, a heavier and even more elusive cousin of the known neutrinos. Or perhaps it is part of a whole, hidden, dark sector of particles and forces that interacts with our own visible world only through very weak or portal interactions. Another profound and equally challenging mystery is the nature of antimatter. According to the laws of physics, the Big Bang should have produced matter and antimatter in almost perfectly equal amounts. But when a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy. If the early universe had been perfectly symmetric, all the matter and antimatter would have been destroyed, leaving behind a cold, empty universe filled with nothing but photons. The very fact that we exist, that the universe is filled with galaxies, stars, and planets made of matter, is a testament to a deep and as yet unexplained asymmetry in the laws of nature. In the first moments of the universe, for some reason, a tiny excess of matter was created about one extra particle of matter for every billion particle-antiparticle pairs. All the substance of our universe is the leftover remnant of this primordial symmetry-breaking event. The Standard Model does contain a small amount of CP violation, a subtle difference in the way matter and antimatter behave. But it is far too small to account for the observed dominance of matter in the cosmos. There must be a new source of CP violation, a new physics beyond the Standard Model, that is responsible for our very existence. The LHC is searching for this new physics by studying the decays of certain rare particles, like B mesons, with incredible precision, looking for any tiny deviation from the predictions of the Standard Model that could signal a new asymmetric interaction. And then there is the ultimate challenge, the holy grail of modern physics, the unification of gravity with quantum mechanics. The Standard Model is a quantum theory, but it does not include gravity. Einstein's general theory of relativity is our best theory of gravity, but it is a classical theory. The search for a quantum theory of gravity that can consistently describe both the very large and the very small is the great unfinished revolution of 20th century physics. Some theories, like string theory, propose a radical solution, the existence of extra hidden dimensions of space. In these theories, the weakness of gravity compared to the other forces could be explained by the fact that gravity is the only force that can leak out into these extra dimensions. The LHC is searching for evidence of these extra dimensions by looking for the production of microscopic black holes or for the signature of Kaluza-Klein particles, the heavy copies of the known particles that would be the result of their vibration in the extra dimensions. The absence of answers to these profound questions is not a sign of failure. It is a sign that we are standing at the threshold of a new and deeper understanding of the universe. The LHC, with its ongoing upgrades and its ever-increasing precision, remains our most powerful tool for probing this new frontier. It is a machine that is designed not just to find answers, but to ask new and more profound questions. And in the subtle anomalies, the unexpected results, the things that don't fit our current theories, may lie the clues that will lead us to the next great revolution in our understanding of the deep, beautiful, and wonderfully mysterious nature of reality. The Standard Model of particle physics is one of the crowning achievements of modern science. It is a beautiful and remarkably successful theory that describes the fundamental subatomic constituents of our universe and the forces that govern their interactions. It is a testament to the power of human reason to uncover the deep mathematical order that underlies the seeming chaos of the physical world. At its core, the Standard Model is a kind of periodic table of the fundamental particles. It organizes the known particles into three fundamental categories. The first are the quarks, which are the building blocks of the protons and neutrons that make up the atomic nucleus. There are 6 flavors of quarks, which come in 3 generations of increasing mass: the up and down quarks, the charm and strange quarks, and the top and bottom quarks. The second category are the leptons, which are the other fundamental matter particles. The most famous of these is the electron, which orbits the atomic nucleus and is responsible for all of chemistry. The electron also has 2 heavier cousins, the muon and the tau, and each of these 3 charged leptons has a corresponding, nearly massless and incredibly elusive partner, the neutrino. The third category are the gauge bosons, which are the particles that mediate the fundamental forces of nature. The photon is the carrier of the electromagnetic force. The gluons are the carriers of the strong nuclear force, the force that binds the quarks together inside protons and neutrons. And the W and Z bosons are the carriers of the weak nuclear force, the force that is responsible for certain kinds of radioactive decay. And finally, there is the Higgs boson, the particle associated with the all-pervading Higgs field, which, as we have seen, is responsible for giving mass to many of the other fundamental particles. This elegant and relatively simple cast of 17 fundamental particles and the mathematical framework of quantum field theory that describes their interactions has been able to explain, with incredible precision, the results of virtually every particle physics experiment that has ever been performed. It is a theory that has been tested and confirmed to an astonishing degree of accuracy. And yet, for all its success, we know that the Standard Model is not the final word. It is an incomplete theory, a beautiful but partial chapter in the grand book of reality. It has a number of profound and glaring omissions. Most famously, it does not include the force of gravity. It has no explanation for the existence of dark matter and dark energy, the mysterious, invisible components that make up 95% of the energy content of the universe. It does not explain the observed asymmetry between matter and antimatter. And it has a number of free parameters, about 19 of them, like the masses of the particles and the strengths of the forces, whose values are not predicted by the theory, but must be measured experimentally. These are not just minor details. They are deep conceptual cracks in the foundation of our current understanding, cracks that point towards the existence of a new and more fundamental layer of physical reality. The search for this new physics beyond the Standard Model is the primary occupation of modern experimental and theoretical particle physics, and there are a number of compelling theoretical ideas that offer a glimpse of what this new physics might look like. One of the most elegant and most popular of these is the idea of supersymmetry, or SUSY. Supersymmetry is a hypothetical new symmetry of nature that would relate the 2 fundamental classes of particles, the fermions, which are the matter particles like quarks and leptons, and the bosons, which are the force-carrying particles. In a supersymmetric world, every known fermion would have a corresponding superpartner boson, and every known boson would have a corresponding superpartner fermion. The electron would have a superpartner called the selectron. The quark would have a squark. The photon would have a photino. The Higgs boson would have a Higgsino. This doubling of the particle zoo may seem like a complication, but it is a complication that has the potential to solve a number of the deep problems of the Standard Model at once. For example, the existence of these new supersymmetric particles would naturally and elegantly solve the hierarchy problem, the puzzle of why the Higgs boson is so light. The quantum corrections to the Higgs mass from the Standard Model particles would be almost perfectly cancelled by the contributions from their superpartners, keeping the Higgs mass naturally small and stable. Supersymmetry also provides a natural candidate for the dark matter particle. In most supersymmetric models, the lightest supersymmetric particle is stable, and it would have just the right properties, being massive and interacting only weakly with normal matter to be the dark matter that we observe in the cosmos. And finally, at very high energies, the strengths of the three forces of the Standard Model, when extrapolated using the equations of supersymmetry, seem to converge to a single, unified value, a tantalizing hint of a grand unified theory where the three forces are just different aspects of a single underlying force. For all these reasons, the search for supersymmetry has been one of the primary goals of the Large Hadron Collider. But after more than a decade of searching, the LHC has, so far, found no evidence for these new supersymmetric particles. This has led many to question the validity of the simplest and most natural supersymmetric models, and to explore other, more complex, or more hidden versions of the theory. Another and equally profound idea for physics beyond the Standard Model is the existence of extra hidden dimensions of space. As we have seen, theories like string theory require the existence of 10 or 11 space-time dimensions to be mathematically consistent. The idea is that the extra spatial dimensions are compactified, curled up into a tiny, and for us, invisible shape. But these extra dimensions could have real and potentially detectable physical consequences. They could help to explain the weakness of gravity, and they could provide a home for new particles and new forces. The search for these extra dimensions at the LHC is a search for strange and unexpected experimental signatures, like the production of microscopic black holes, or the observation of a tower of heavy Kaluza-Klein particles, which would be the extra-dimensional copies of the known Standard Model particles. And then there is the possibility of entirely new, and as yet unimagined, fundamental forces and particles. The Standard Model has a very specific and somewhat arbitrary structure. There is no deep theoretical reason why there should be exactly 3 generations of quarks and leptons, or why the forces should have the specific mathematical structure that they do. It is possible that there is a whole new dark sector of particles and forces that is hidden from us, a sector that interacts with our own visible world only through very weak or portal interactions. Dark matter could be a part of this dark sector, and the LHC, with its high energies and its incredible sensitivity, is a powerful tool for searching for the subtle, indirect signatures of this hidden world. The absence of any clear, unambiguous signal of new physics at the LHC beyond the Higgs boson has been a source of both frustration and excitement in the particle physics community. It is frustrating because the simple and elegant solutions to the problems of the Standard Model, like supersymmetry, have not yet materialized. But it is also exciting because it means that the universe is more subtle, more clever, and more mysterious than we thought. The path to a deeper understanding is not as straightforward as we might have hoped, and it will require a new generation of more powerful experiments, and perhaps a new generation of even more creative and more radical theoretical ideas. The story of the universe is far from over, and the Standard Model, for all its beauty and its success, is just the beginning of the story. The idea that our familiar or four-dimensional universe may be just a small slice of a much larger and much more complex. Multidimensional reality is one of the most mind-bending and transformative concepts in all of modern physics. It is an idea that has its roots in the early 20th century, but it has been given a new and powerful life by the development of modern unified theories like string theory. The quest to unify gravity with the other forces of nature has led physicists down a path that seems to inevitably point towards the existence of extra hidden dimensions of space. In string theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. And the mathematical consistency of this theory requires that these strings must be vibrating in a space-time that has more than the 4 dimensions we are familiar with, typically 10 or 11 dimensions in total. So, where are these extra dimensions? Why do we not see them in our everyday lives? The standard answer is that they are compactified, curled up into a tiny, intricate, and for us, invisible, geometrical shape at every point in our 3-dimensional space. Imagine a tightrope walker from a great distance. The rope appears to be a one-dimensional line. The walker can only move forwards or backwards. But for a tiny ant on the rope, there is another and very real dimension, the circular dimension that goes around the rope. The ant can move forwards and backwards, but it can also move around the rope. The extra dimensions of string theory are like this circular dimension of the rope, but they are curled up on a scale that is unimaginably small, the Planck length, which is why we do not perceive them directly. But these extra dimensions are not just a mathematical curiosity. They have profound physical consequences. The precise shape and size of this compact, 6 or 7-dimensional Calabi-Yau manifold is what determines the properties of the strings, and therefore, the properties of all the particles and forces of our universe. The laws of physics are a reflection of the geometry of these hidden dimensions. This is a breathtakingly beautiful and ambitious idea. It suggests that the deep, and often seemingly arbitrary, structure of our universe is a consequence of a hidden, higher dimensional geometry. But the existence of extra dimensions has also led to another, and equally radical, idea: the Brainworld scenario. In this picture, our entire 4-dimensional universe is a brain, a subspace that is floating in a higher dimensional bulk. The particles and forces of the Standard Model are confined to our brain. They are like drawings on a sheet of paper that cannot leave the surface. But gravity, the geometry of space-time itself, is a property of the entire higher dimensional bulk, and it is free to propagate through the extra dimensions. This could provide a beautiful and elegant solution to the hierarchy problem. The puzzle of why gravity is so much weaker than the other forces. The gravitational force is not intrinsically weak. It just appears weak to us because its influence is being diluted, spread out over the extra hidden dimensions. Our brain is only feeling a small fraction of its true higher dimensional strength. The Brainworld scenario opens up a host of new and truly extraordinary cosmological possibilities. There could be other parallel brains, other universes, floating nearby in the bulk, separated from us by a tiny distance in a 5th dimension. This is a different kind of multiverse than the bubble universe picture of eternal inflation. It is a multiverse of stacked, parallel realities. And it is a multiverse that could, in principle, have observable consequences. While we cannot directly travel to these other brains, we could potentially interact with them through the one force that can travel through the bulk gravity. The mysterious, invisible dark matter that fills our universe could be the gravitational influence of ordinary matter that is confined to a nearby parallel brain. We cannot see the matter on that shadow brain because light and the other Standard Model forces are trapped on it. but we can feel its gravitational pull. The Big Bang itself could have been the result of a collision between our brain and another, a cataclysmic event in the higher dimensional bulk that released the energy to create our entire cosmos. This ekpyrotic, or cyclic model, as we have seen, provides a compelling alternative to the standard inflationary picture of our cosmic origin. The search for evidence of these extra dimensions is one of the most exciting and active frontiers of modern experimental physics. The Large Hadron Collider is at the forefront of this search. If the extra dimensions are large enough, then the high-energy collisions at the LHC could have enough energy to kick a particle off of our brain and into the bulk. This would manifest in the detectors as missing energy, a clear and unambiguous signal that something has escaped from our familiar four-dimensional world. The LHC could also, in some of these models, have enough energy to create tiny, microscopic black holes. These would not be the dangerous, galaxy-devouring black holes of astrophysics. They would be tiny, fleeting, quantum gravitational objects that would evaporate almost instantly in a shower of Hawking radiation. The detection of such an event would be a stunning and Nobel Prize-winning confirmation of the existence of extra dimensions and a direct window into the strange and beautiful world of quantum gravity. So far, the LHC has found no evidence for either missing energy or microscopic black holes. This has placed tight constraints on many of the simplest and most natural extra-dimensional models, but the search continues. The universe may be more subtle, more clever, and more multidimensional than we have yet been able to probe. The idea of hidden dimensions is a concept that pushes the limits of our scientific imagination. But it is an idea that is born from the deep, mathematical logic of our best and most ambitious physical theories. And it is an idea that reminds us that the reality we perceive with our senses may just be a shadow, a fleeting and partial projection of a much richer, much deeper, and much more wonderfully complex multidimensional cosmos. The idea of a multiverse, a vast and perhaps infinite ensemble of other parallel universes, is one of the most breathtaking, most mind-altering, and also most controversial concepts in all of modern science. It is an idea that has migrated from the pages of science fiction to the blackboards of our most eminent theoretical physicists. And it is an idea that has the potential to fundamentally reshape our understanding of our own cosmic place. The multiverse is not a single, coherent theory, but is a concept that arises in different forms from several of our deepest and most successful physical theories. The many worlds interpretation of quantum mechanics, as we have seen, suggests a constantly branching quantum multiverse, where every possible outcome of every quantum event is realized in a separate, parallel reality. The theory of eternal inflation suggests a bubble universe multiverse, where our own cosmos is just one, local, post-inflationary bubble in a much larger and eternally inflating meta-universe. And the landscape of string theory suggests a multiverse of different possible vacuum states, each with its own unique set of physical laws and constants. While the details of these different multiverse scenarios differ, they all share a common and deeply revolutionary idea that our universe is not the whole of reality. It is just one, small, and perhaps insignificant, part of a much larger and much more diverse cosmic tapestry. This is a vision that is both humbling and intellectually powerful. It is humbling because it represents the final and most profound step in the Copernican revolution, the long historical process of decentering humanity from a special and privileged position in the cosmos. We are not at the center of the solar system. We are not at the center of the galaxy, and we may not even be in the only universe. But the multiverse is also intellectually powerful because it provides a potential scientific explanation for one of the deepest and most puzzling features of our own universe, its apparent and seemingly miraculous Fine-tuning for the existence of life, the anthropic principle, in the context of a multiverse, becomes a simple and powerful selection effect. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves on a planet that is hospitable to life. We could not have found ourselves anywhere else but the primary and most serious. Objection to the multiverse hypothesis is that it is, by its very nature, untestable. We can never, even in principle, travel to another bubble universe or communicate with a parallel quantum branch. The multiverse seems to lie forever beyond the reach of our direct empirical science. This has led many to argue that the multiverse is not a scientific theory at all, but is a form of metaphysical speculation, a new and more sophisticated version of the ancient religious and philosophical myths of creation. They argue that by embracing an untestable theory, we are in danger of abandoning the very principles of empirical verification that have been the hallmark of the scientific revolution. We are in danger of turning science into a new kind of dogmatic faith. Others, however, argue that this is a naive and overly restrictive view of the scientific method. They argue that a theory should be judged not just by its direct empirical predictions, but also by its explanatory power, its mathematical consistency, its elegance, and its ability to solve the deep conceptual puzzles of our current theories. The multiverse, they argue, for all its strangeness and its untestability, does provide a powerful and perhaps the only naturalistic explanation for the apparent fine-tuning of the physical constants of our universe. In this view, the multiverse is not just a wild speculation. It is a logically necessary consequence of our best current understanding of cosmology and quantum mechanics. The LHC could provide hints of the multiverse in several different ways. The search for extra dimensions is, in a sense, a search for the multiverse. If the LHC were to discover evidence of extra dimensions through the production of microscopic black holes or the detection of missing energy, it would lend powerful circumstantial support to the Brainworld scenario, a specific and well-defined model of a multiverse. The properties of the Higgs boson itself could also provide a clue. As we have seen, the measured mass of the Higgs seems to place our universe in a metastable vacuum state. In the context of the string theory landscape, this is exactly what one might expect. The vast majority of the possible vacuum states in the landscape are not stable. And so, if universes are populated randomly across this landscape, we should not be surprised to find ourselves in a universe that is long-lived, but not eternally stable. The metastability of our vacuum could be a sign that we are living in a multiverse. The search for new and unexpected particles and forces at the LHC is also a search for the multiverse. If the LHC were to discover a new, long-lived particle or a new, very weak force, it could be a sign of a hidden, dark sector of particles that interacts with our own visible world only very weakly. And this dark sector could be the matter of a nearby parallel brane or a portal to a different hidden reality. The most direct and also most speculative way that the LHC could probe the multiverse is through the potential production of microscopic black holes. In some Brainworld models with large extra dimensions, the energy required to create a black hole is much lower than in our familiar four-dimensional spacetime. It is possible that the high-energy collisions at the LHC could have enough energy to create tiny, fleeting quantum black holes. These black holes would not be dangerous. They would evaporate almost instantly in a shower of Hawking radiation. But the specific properties of this radiation, its temperature, its spectrum, could provide us with a direct window into the physics of the extra dimensions, and perhaps even into the nature of quantum gravity itself. So far, the LHC has found no evidence for any of these exotic, multiverse-related phenomena. This has placed tight constraints on many of the simplest and most natural multiverse models, but the search is far from over. The upcoming high luminosity upgrade of the LHC will increase its sensitivity to rare processes by a factor of 10, opening up a new and much wider window of discovery. And the next generation of even more powerful colliders, like the proposed Future Circular Collider, will push the energy frontier even further. The multiverse is an idea that is on the very edge of our scientific knowledge. It is a concept that is as beautiful and as profound as it is controversial and untestable. It may be that we will never find a definitive, smoking gun proof of its existence. But the search itself, the quest to understand whether our universe is the one and only, or just one of a vast and perhaps infinite cosmic ensemble, is a quest that is at the very heart of the human scientific adventure. It is a quest that is pushing our theories, our experiments, and our very imagination to their ultimate limits. The mysterious, invisible substance known as dark matter is one of the most profound, and also most humbling, puzzles in all of modern science. It is a substance that makes up about 85% of the total matter in the universe, and yet we have no idea what it is. It is the silent, gravitational scaffolding upon which the entire, visible structure of our cosmos is built. And yet, it remains completely and stubbornly invisible to all of our most powerful telescopes. The evidence for the existence of dark matter is overwhelming, and it comes from a host of different and independent astronomical observations. It was first inferred in the 1930s by the Swiss astronomer Fritz Zwicky, who observed that the galaxies in the Coma cluster were moving far too fast to be held together by the gravity of their visible stars alone. He concluded that there must be a huge amount of unseen, dark matter providing the extra gravitational glue. In the 1970s, the American astronomer Vera Rubin made the same startling discovery when she studied the rotation speeds of individual spiral galaxies. She found that the stars in the outer regions of these galaxies were orbiting far too quickly. According to Newton's laws of gravity, their speeds should have dropped off with distance from the galactic center. But they did not. They remained stubbornly high. The only way to explain this was to posit the existence of a vast and invisible halo of dark matter surrounding each galaxy. A halo whose gravitational pull was keeping the outer stars in their high-speed orbits. Since then, the evidence has continued to mount. The way that the gravity of massive galaxy clusters bends and distorts the light from more distant background galaxies, a phenomenon known as gravitational lensing, provides a direct way to map the distribution of mass, and it has confirmed the existence of these vast dark matter halos. The temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, also carry a clear and precise imprint of the amount of dark matter in the early universe. All of these different lines of evidence converge on a single and inescapable conclusion: the universe is filled with a new, and as yet undiscovered, form of matter. A matter that does not interact with light. A matter that is dark. But what is it the standard model of particle physics? Our otherwise incredibly successful theory of the fundamental particles and forces has no place for a dark matter particle. This means that dark matter must be something new, something that lies beyond our current and well-tested understanding of reality. For decades, the leading candidate for the dark matter particle was the weakly interacting massive particle, or WIMP. This was a generic term for a new heavy particle that would interact with normal matter only through the weak nuclear force and gravity. This was an attractive idea for a number of reasons. Firstly, theories beyond the standard model, like supersymmetry, naturally predicted the existence of new, stable, and weakly interacting particles with just the right properties to be the dark matter. And secondly, a WIMP with a specific mass and interaction strength would have been produced in the hot early universe in just the right abundance to account for the observed amount of dark matter today. This WIMP miracle, as it was called, made it the focus of an intense and worldwide experimental search. But after decades of searching, in deep underground laboratories with satellite-based telescopes, and at the Large Hadron Collider, we have found no definitive evidence for WIMPs. The parameter space for the simplest and most natural WIMP models has been almost completely ruled out. This has led to a crisis in the field of dark matter physics, a crisis that has also been a period of immense creative ferment. Physicists are now exploring a whole host of new and more exotic dark matter candidates. Perhaps dark matter is not a WIMP, but an action, a hypothetical, ultralight particle that was originally proposed to solve a different puzzle in the theory of the strong nuclear force. Actions would be incredibly difficult to detect, as they interact with normal matter even more weakly than WIMPs, but a number of clever new experiments are being designed to search for their faint, telltale signature. Or perhaps dark matter is not a single particle, but is part of a whole, hidden dark sector. A complex world of dark particles and dark forces that interacts with our own visible world only through a faint, gravitational portal. The Large Hadron Collider is one of the most powerful tools we have in the search for dark matter. While it may not be able to detect a dark matter particle directly, as these particles would fly straight through the detectors without leaving a trace, it can search for them indirectly. If dark matter particles are produced in the high-energy collisions at the LHC, they will carry away energy and momentum. This would manifest in the detectors as missing energy, a clear and unambiguous imbalance in the energy of the visible particles that are produced in the collision. The search for this missing energy signature is one of the highest priorities of the LHC experimental program. So far, no such signal has been seen, which has placed tight constraints on many dark matter models. But the search continues. And with the upcoming high luminosity upgrade of the LHC, the sensitivity to these kinds of signatures will be dramatically increased. A more radical and more controversial idea is that dark matter may not be a particle at all. Perhaps our understanding of gravity is wrong. The theory of modified Newtonian dynamics, or MOND, proposes that Newton's law of gravity needs to be modified at very low accelerations, like those found in the outer regions of galaxies. In this view, there is no dark matter. The observed anomalous rotation of galaxies is simply a sign that gravity is stronger than we thought in these regimes. While MOND has had some remarkable successes in explaining the rotation curves of individual galaxies, it has struggled to explain the observations of galaxy clusters and the cosmic microwave background without invoking some form of dark matter. The mystery of dark matter is not just a puzzle for particle physicists and astronomers. It is a profound philosophical challenge to our understanding of reality. It is a humbling reminder that the world we see, the world of stars, of planets, of light, is just a small, and perhaps insignificant, fraction of the true cosmic reality. We are living in a universe whose primary material constituent is completely unknown to us. But could the mystery of dark matter be connected to another, and even deeper, mystery, the existence of parallel universes? This is a speculative but deeply intriguing idea. In the Brainworld scenarios we have discussed, our universe is a three-dimensional membrane floating in a higher dimensional space. In some of these models, there could be other parallel branes nearby, and it is possible that the dark matter we observe is simply the gravitational influence of ordinary matter that is confined to one of these nearby shadow branes. We cannot see the matter on that other brane, because light and the other standard model forces are trapped on it. But we can feel its gravity, because gravity is a property of the entire higher dimensional bulk. In this view, dark matter is not a new, exotic particle. It is a ghost, a gravitational echo of a whole other universe that is existing just a hair's breadth away from our own. This is a breathtaking and almost poetic idea. It would mean that the invisible halo of dark matter that surrounds our own galaxy is not just a cloud of unknown particles. It is the gravitational shadow of a parallel, and perhaps even identical, Milky Way galaxy. A galaxy that is sharing our corner of the higher dimensional cosmos. The search for the nature of dark matter is one of the great scientific adventures of our time. It is a quest that is being pursued on multiple fronts, from the deep underground laboratories searching for a single, fleeting particle interaction, to the vast cosmological surveys mapping the large-scale structure of the universe, to the high-energy collisions at the Large Hadron Collider. The resolution of this mystery, whatever it may be, will undoubtedly mark a new and revolutionary chapter in our understanding of the universe, and it is a mystery that serves as a constant and powerful reminder of the vastness of our own ignorance and of the deep, dark, and beautiful secrets that are still waiting to be discovered in the silent, gravitational whispers of the cosmos. The Large Hadron Collider, in its first decade-long run, has been a story of both spectacular triumph and profound and puzzling silence. The triumph, of course, was the discovery of the Higgs boson in 2012, the final missing piece of the standard model of particle physics. A discovery that confirmed our understanding of the origin of mass and completed the beautiful and remarkably successful theoretical edifice that has been built over the last half-century. But the silence has been just as profound. In the years since the Higgs discovery, the LHC has been pushed to higher and higher energies and has collected an immense amount of data. And yet it has so far found no definitive evidence for any of the new physics beyond the standard model that was so confidently predicted by theorists. Supersymmetry, extra dimensions, microscopic black holes, new forces, new particles, all of the elegant and well-motivated. Theoretical solutions to the deep, remaining puzzles of the universe have, so far, failed to materialize. This has led to a period of deep soul-searching, of re-evaluation, and also of immense creative excitement in the world of particle physics. We are standing at a crossroads, a moment where the old, familiar map of reality has run out, and we are venturing into a truly uncharted territory. The search for supersymmetry, or SUSY, has been one of the primary drivers of the LHC experimental program. The theory, as we have seen, is a beautiful and elegant one, and it has the potential to solve a number of the deep problems of the standard model at once, but the simplest and most natural. Versions of supersymmetry predicted that the superpartner particles should have masses that were within the reach of the LHC. The fact that we have not seen them is a major puzzle. This does not necessarily mean that supersymmetry is wrong. It could be that the superpartners are much heavier than we thought and are simply beyond the reach of the current LHC, or it could be that supersymmetry is a more complex and more hidden symmetry than our simplest models predicted. But the absence of any evidence for SUSY has forced physicists to consider other and more unconventional solutions to the hierarchy problem, the puzzle of the Higgs mass, another major and so far fruitless. Search at the LHC has been the search for a particle candidate for dark matter. The WIMP paradigm, which was the leading theoretical framework for decades, has been severely constrained by the lack of any signal at the LHC and in the deep, underground direct detection experiments. This has led to a paradigm shift in the field of dark matter physics, a shift away from the simple, WIMP-centric view and towards a much broader and more diverse landscape of possibilities. The search is now on for actions, for sterile neutrinos, for dark photons, for a whole, hidden, dark sector of particles and forces. This is a much more challenging search, as these new candidates are often much lighter and interact even more weakly than WIMPs, making their signatures at the LHC much more subtle and difficult to detect. But it is a search that is being pursued with a new sense of creativity and urgency. The Higgs boson itself, while a monumental discovery, has also presented us with a new set of puzzles. Its measured properties are, so far, remarkably consistent with the predictions of the Standard Model. It seems to be a simple, garden-variety Higgs. But is this the whole story? Or is the Higgs boson a portal to a new and hidden sector of physics? Some theories suggest that there could be multiple types of Higgs bosons, a whole Higgs family. Others suggest that the Higgs boson could interact with new, as yet undiscovered, particles, like those of the dark matter sector. The precision study of the properties of the Higgs boson, its mass, its spin, its interactions with all the other known particles, is one of the primary goals of the ongoing LHC program. Any tiny deviation from the predictions of the Standard Model could be the first telltale sign of the new physics that we know must be there. To push the boundaries of this search, the LHC itself is undergoing a major and ambitious upgrade. The High Luminosity LHC, which is scheduled to begin operations in 2029, will not increase the energy of the collider, but will dramatically increase its luminosity, which is a measure of the number of particle collisions that occur per second. The HL-LHC will increase the luminosity by a factor of 10, allowing the experiments to collect a data set that is 10 times larger than the current one. This will be a game changer. It will allow physicists to study extremely rare processes that have never been seen before. It will allow for a much more precise measurement of the properties of the Higgs boson and of the other known particles, and it will dramatically increase the sensitivity of the search for new, high-mass particles and for the subtle, indirect signatures of new physics. The HL-LHC is a machine that is designed to search for the small cracks in the beautiful, but ultimately incomplete edifice of the Standard Model. But what if the HL-LHC, too, finds nothing new? What if the universe is more subtle, more well-hidden, than even this powerful new machine can reveal? This is a possibility that the physics community is now beginning to seriously grapple with, and it has led to the planning of the next generation of even larger and more powerful particle colliders. The Future Circular Collider is one such proposal, a massive 100-kilometer ring that would be capable of reaching collision energies that are nearly 10 times higher than the LHC. Another complementary proposal is the International Linear Collider, a machine that would collide electrons and their antimatter counterparts, positrons, with incredible precision. A linear collider would not reach the same raw energies as a large circular proton collider like the FCC, but it would provide a much cleaner experimental environment, allowing for incredibly precise measurements of the properties of particles like the Higgs boson. The future of particle physics is at a crossroads. The easy, low-hanging fruit of the Standard Model has been picked. The path forward, into the deep and largely unknown territory beyond the Standard Model, is likely to be a long and challenging 1. It will require a new generation of more powerful machines, a new level of global collaboration, and perhaps a new and more radical way of thinking about the fundamental nature of reality. But it is a journey that we must take. The mysteries of dark matter, of quantum gravity, of the origin of our own material existence are too deep, too profound, and too beautiful to be left unanswered. The LHC has opened a new window onto the universe, and what we have seen so far is just a glimpse of the vast and wonderfully mysterious landscape that still lies ahead. The Large Hadron Collider has already reshaped our understanding of the universe, but its next phase, the high luminosity LHC, promises to push the boundaries of physics even further. Scheduled to become fully operational in 2029, this ambitious upgrade represents the next evolution in particle physics experimentation. This upgrade will not just increase the energy of the collisions, but will dramatically enhance the luminosity of the collider, a measure of the number of particle collisions that can be produced per second. The HL-LHC will increase the collision rate by a factor of 10, allowing the experiments to collect a dataset that is 10 times larger than all the data collected in the first decade-long run of the LHC. This is a crucial step forward. In the world of high-energy physics, more data translates directly to more precision, and more precision translates to a greater chance of discovering new and subtle physical phenomena. Many of the processes that are predicted by theories beyond the standard model, such as the production of supersymmetric particles or the effects of extra dimensions, are expected to be extremely rare, occurring perhaps only once in every trillion collisions. To have any hope of observing these fleeting events, scientists need to create a truly astronomical number of collisions. The HL-LHC is a machine that is designed to do exactly that. It is a rare process factory, a powerful tool designed to search for the proverbial needle in a cosmic haystack. One of the primary scientific goals of the HL-LHC is to study the Higgs boson with unprecedented precision. The discovery of the Higgs in 2012 was a monumental achievement, but it was just the beginning of the story. We know that the Higgs boson exists, but we still know very little about its true nature. Is it a single, fundamental particle, as the standard model predicts, or is it a composite object made of other, more fundamental constituents? Is it part of a larger, more complex Higgs sector with other, as yet undiscovered, Higgs-like particles? The HL-LHC will allow physicists to measure the properties of the Higgs, its mass, its spin, its interactions with all the other known particles, with a precision that is an order of magnitude better than what is currently possible. Any tiny deviation from the predictions of the standard model would be a smoking gun signal of new physics, a window into the reality that lies beyond our current understanding. The HL-LHC will also dramatically increase our sensitivity to the search for new, high-mass particles. If theories like supersymmetry are correct, but the new superpartner particles are simply too heavy to have been produced in significant numbers at the current LHC. The huge increase in the number of collisions at the HL-LHC will give us a much better chance of seeing them. The search for the elusive dark matter particle will also be a major focus of the HL-LHC program. The upgraded collider will be able to search for a much wider range of dark matter candidates, and with much greater sensitivity than the current LHC. The search for the missing energy signature of dark matter production will be pushed to new limits, and new, more subtle. Search strategies will be employed to try and catch a glimpse of this invisible and mysterious component of our universe. The technological challenges of upgrading the LHC to its high luminosity configuration are immense. It is a project that is pushing the very limits of modern accelerator and detector technology. It requires the development of new, more powerful, and more compact superconducting magnets to focus the proton beams down to an even smaller size at the collision points. It requires a new generation of Crab cavities, a special kind of radio frequency cavity that can tilt the proton bunches just before they collide to maximize their overlap and the collision rate. And it requires a complete and ambitious. Upgrade of the giant detectors, ATLAS and CMS. These detectors will need to be equipped with new, more granular, and more radiation-resistant sensors that can handle the incredible and unprecedented data rates of the HL-LHC. This is a monumental engineering endeavor, an endeavor that is requiring a new level of innovation, of ingenuity, and of global scientific collaboration. But the potential scientific payoff is enormous. The HL-LHC will be one of the most important scientific projects of the coming decades. A machine that has the potential to rewrite the laws of physics and to answer some of the most fundamental questions about the nature of our universe. It may be the machine that finally discovers the dark matter particle, that finds the first evidence of supersymmetry, that reveals the existence of extra dimensions, or that uncovers a whole new and completely unexpected layer of physical reality. But even if the HL-LHC finds nothing new, even if the standard model continues to hold up to every new and more precise test, that in itself would be a profound and deeply puzzling result. It would mean that the solutions to the deep problems of the standard model lie at an energy scale that is far beyond the reach of any conceivable future accelerator. It would mean that we may need a completely new and more radical theoretical paradigm to make progress. It might even mean that we are beginning to approach a fundamental limit to our ability to probe the universe with our current reductionist methods. The HL-LHC is a bet, a bold and ambitious bet on the future of particle physics. It is a bet that the universe still has new and discoverable secrets to reveal at the energy scale that we can access. And it is a bet that the human quest for knowledge, for a deeper understanding of our cosmic home, is a journey that is still far from over. The discoveries that are made at the HL-LHC in the coming decades will undoubtedly reshape our understanding of the universe in ways that we cannot yet imagine, and will set the course for the next generation of scientific exploration. The quest to understand the fundamental nature of reality is a journey that will not end with the Large Hadron Collider, or even with its high luminosity upgrade. The human spirit of discovery is a relentless one, and physicists are already dreaming of and planning for the next generation of even larger and more powerful scientific instruments, machines that will be able to push the frontiers of our knowledge to new and currently unimaginable energy scales. One of the most ambitious of these proposals is the Future Circular Collider, a project that is currently being studied at CERN. The FCC would be a true scientific behemoth, a 100-kilometer-long underground ring, almost 4 times the size of the current LHC. Such a machine would be capable of reaching collision energies that are about 7 times higher than the LHC, opening up a vast and largely unexplored new territory for discovery. The FCC is envisioned as a multi-stage project. The first stage would be an electron-positron collider, a Higgs factory that would be able to produce millions of Higgs bosons in a very clean and well-understood experimental environment. This would allow for incredibly precise measurements of the properties of the Higgs, a search for any tiny deviation from the predictions of the standard model that could signal the existence of new physics. The second stage would be a high-energy proton-proton collider, a true discovery machine that would be able to directly search for new heavy particles up to an energy scale that is far beyond the reach of the LHC. If supersymmetry or extra dimensions or a new heavy force of nature exists, the FCC would be our best hope of finding it. Another and complementary proposal is the International Linear Collider, a project that is being championed by a global collaboration of scientists. The ILC would not be a circular machine, but a linear one, about 30 kilometers long, that would collide electrons and positrons with very high precision. A linear collider cannot reach the same raw energies as a large, circular proton collider like the FCC. But it has a key advantage: the collisions are much cleaner. When protons, which are composite objects made of quarks and gluons, collide, they create a very messy and complex spray of particles, an electron-positron collision. On the other hand is a much simpler and more well-defined interaction, which allows for incredibly precise measurements of the properties of the particles that are produced. The ILC would be a powerful precision tool for studying the Higgs boson and for searching for the subtle, indirect signatures of new physics. But the future of fundamental physics is not just about building bigger and bigger colliders. It is also about exploring new and more innovative ways to probe the secrets of the universe. The growing field of astroparticle physics is a beautiful example of this. It is a field that uses the universe itself as a laboratory. High-energy cosmic rays, neutrinos, gamma rays, gravitational waves. These are the particles that are produced in the most extreme and energetic environments in the cosmos. In supernovae, in neutron star collisions, in the hearts of active galaxies. By studying these cosmic messengers with a new generation of powerful ground-based and space-based detectors, we can probe the laws of physics at energies and in conditions that are far beyond the reach of any terrestrial accelerator. The search for the nature of dark matter is a prime example of this synergistic approach. While the LHC is searching for the production of dark matter particles in high-energy collisions, a host of other experiments are searching for them in different ways. Deep, underground detectors are trying to catch the rare, fleeting signal of a dark matter particle from our galaxy's halo bouncing off an atomic nucleus. Telescopes are searching for the faint, gamma-ray glow of dark matter particles annihilating each other in the dense center of our galaxy. And cosmological surveys are mapping the distribution of dark matter on the largest scales, providing crucial clues to its properties and its history. The quest to unify gravity and quantum mechanics is another area where a multi-pronged approach is essential. While a future, high-energy collider may one day find the first direct evidence of new quantum gravitational physics, our best hope for probing this realm in the near future may come from the precision study of the cosmos itself. The search for the faint, primordial signature of gravitational waves from the period of cosmic inflation in the cosmic microwave background is a direct window into the physics of the very early and very high-energy universe, and the study of black holes, both with electromagnetic telescopes and with gravitational wave detectors, is providing us with a unique and powerful laboratory for testing the predictions of general relativity in the strong field regime, the very place where we expect the first subtle signs of its breakdown to appear. And finally, the future of fundamental physics will be increasingly intertwined with the development of new and more powerful computational tools. The vast amounts of data that will be generated by the next generation of experiments will require a new level of computational power and a new generation of sophisticated, AI-driven algorithms to analyze. And the development of practical, large-scale quantum computers could, one day, revolutionize the field of theoretical physics, allowing us to perform simulations of complex quantum systems, like the dynamics of a quark-gluon plasma or the quantum geometry of spacetime itself, that are completely intractable on a classical computer. The future of our quest to understand the universe is a bright and incredibly exciting one. It is a future that will be driven by a rich and diverse ecosystem of different and complementary, experimental and theoretical approaches. It is a future that will require a new level of global collaboration, of long-term vision, of scientific creativity. And it is a future that holds the promise of answering some of the deepest, most profound, and most beautiful questions that humanity has ever asked. The idea of a multiverse, a vast and perhaps infinite ensemble of other parallel universes is one of the most breathtaking, most mind-altering, and also most controversial concepts in all of modern science. It is an idea that pushes the very limits of our imagination and also of our scientific methodology. If these other universes exist, they are, by their very nature, likely to be forever beyond the reach of our direct observation and experimentation. And so, the question arises if the multiverse is a theory that can never be proven. What does that mean for the future of physics? Does it signal a fundamental limit to our ability to understand the cosmos, or does it require us to adopt a new and more philosophical understanding of what constitutes a scientific theory? The multiverse is not a single, speculative idea that has been pulled out of thin air. It is a concept that arises naturally and almost inevitably from several of our best and most well-tested physical theories. The many worlds interpretation of quantum mechanics, the theory of eternal cosmic inflation, the landscape of string theory, all of these different and well-developed theoretical frameworks seem to point towards the same radical conclusion that our universe is not the one and only. This is a powerful and deeply compelling convergence of ideas. When multiple independent lines of theoretical inquiry all point towards the same surprising conclusion, it is a sign that we should take that conclusion seriously, even if it is a conclusion that challenges our most basic common sense intuitions, but the untestable and perhaps unfalsifiable nature of the multiverse remains a profound and deeply problematic challenge. Science, in its standard form, is a discipline that is based on empirical evidence. A theory is considered scientific to the extent that it makes testable and falsifiable predictions. The multiverse, in its grandest conception, seems to fail this test. This has led to a deep and often contentious debate within the physics and philosophy of science communities. Some argue that the multiverse is not a scientific theory at all, but is a form of metaphysical speculation, a new and more sophisticated version of the ancient religious and philosophical myths of creation. They argue that by embracing an untestable theory, we are in danger of abandoning the very principles of empirical verification that have been the hallmark of the scientific revolution. We are in danger of turning science into a new kind of dogmatic faith. Others, however, argue that this is a naive and overly restrictive view of the scientific method. They argue that a theory should be judged not just by its direct empirical predictions, but also by its explanatory power, its mathematical consistency, its elegance, and its ability to solve the deep conceptual puzzles of our current theories. The multiverse, they argue, for all its strangeness and its untestability, does provide a powerful, and perhaps the only, naturalistic explanation for the apparent fine-tuning of the physical constants of our universe. In this view, the multiverse is not just a wild speculation. It is a logically necessary consequence of our best current understanding of cosmology and quantum mechanics. But what if no evidence, either direct or indirect, for the multiverse is ever found? What if, after decades of searching, the cosmic microwave background remains stubbornly smooth? The LHC finds no sign of extra dimensions or microscopic black holes, and the fundamental constants of nature continue to appear as single, unexplained numbers. This would not necessarily mean that the multiverse does not exist. It could simply mean that its effects are too subtle, too well hidden for our current, and even our future, experiments to detect. But it would undoubtedly lead to a period of deep crisis and reevaluation in theoretical physics. It would force us to confront the possibility that we may have reached a fundamental limit to our ability to probe the ultimate nature of reality. It would force us to ask a difficult and deeply uncomfortable Question: what if the universe is just the way it is, and there is no deeper reason why? This is a possibility that many scientists are reluctant to accept. The entire history of science has been a history of finding deeper and more unified explanations for the phenomena of the natural world. To accept that the fundamental properties of our universe are just a random, accidental set of numbers with no underlying logical or physical explanation seems like a betrayal of the very spirit of the scientific enterprise. It would be a return to a kind of pre-scientific, magical thinking where the world is just a collection of unexplained, brute facts. This is why the search for a final bootstrap theory, a theory of everything that would uniquely and necessarily determine all the properties of our universe, remains such a powerful and enduring dream. But what if this dream is also an illusion? What if the universe is not a unique mathematical necessity, but is in fact just one of a vast and perhaps infinite number of possibilities? The absence of any evidence for the multiverse would not prove that it does not exist, but it would perhaps force us to adopt a new and more humble stance towards our own scientific knowledge. It would force us to accept that there may be certain fundamental questions about the ultimate nature of reality that are, in principle, unanswerable. It would force us to embrace a kind of learned ignorance, a recognition that the universe is not a puzzle to be solved, but a mystery to be lived. The debate over the multiverse is not just a debate about the nature of the cosmos. It is also a debate about the nature of science itself. It is a debate about the limits of our knowledge, about the role of evidence, of theory, of philosophy, of aesthetics, in our quest to understand the universe. And it is a debate that is likely to continue for a long time to come. But whatever the ultimate outcome, the very fact that we are able to have this debate, that we are able to conceive of realities that are so far beyond our own direct experience, is a testament to the remarkable and perhaps even cosmic power of the human mind. The search for the multiverse, whether it ultimately succeeds or fails, is a search that is pushing us to be better scientists, better philosophers, and perhaps even better and more humble human beings. The Large Hadron Collider, in its relentless and powerful probing of the subatomic world, has been a story of both profound discovery and of deep and deepening mystery. The discovery of the Higgs boson in 2012 was a triumph of human ingenuity, a beautiful confirmation of the standard model of particle physics, and a moment that seemed to bring us to the very threshold of a complete understanding of the known, visible universe. But in the years since, the LHC has also given us a profound and puzzling silence. The new physics that was so confidently expected to lie just around the corner, the elegant symmetry of supersymmetry, the strange geometry of extra dimensions, the ghostly particles of dark matter has, so far, failed to appear. This has led some to wonder if we are approaching the end of physics, a point where our current collider-based methodology has reached its fundamental limits. But this is a deeply pessimistic and likely incorrect view. The absence of new discoveries at the LHC is not a sign that there is no new physics to be found. It is a sign that the new physics is more subtle, more well-hidden, and perhaps more strange than our simplest and most natural theories predicted. The universe is not a puzzle that gives up its secrets easily, and the quest to understand it is a long and often winding journey. A journey that is full of both exciting breakthroughs and long periods of patient and often frustrating exploration. The Higgs boson itself, while confirming the standard model, has also opened up a new and largely unexplored landscape of questions. Is it a fundamental, point-like particle, or is it a composite object made of other, more fundamental constituents? Is it the only Higgs boson, Or is it part of a larger, more complex Higgs sector? Does it interact with the mysterious dark sector of the universe? The detailed, precision study of the properties of the Higgs boson is one of the primary goals of the ongoing LHC program and of its upcoming high luminosity upgrade. Any tiny deviation from the predictions of the standard model could be the first telltale sign of the new physics that we know must be there. The mystery of dark matter remains one of the greatest and most humbling challenges in all of science. The failure to find a WIMP particle at the LHC and in the direct detection experiments has forced the field to cast a much wider net, to explore a whole new zoo of more exotic and more difficult to detect dark matter candidates. This is a search that will require a new generation of more sensitive experiments and a new level of creativity and ingenuity from both theorists and experimentalists. And the ultimate mystery, the unification of gravity with quantum mechanics, is a challenge that will likely require a new and more powerful generation of particle accelerators, machines like the proposed Future Circular Collider that can probe the energy scales where the effects of quantum gravity are expected to become apparent. But the future of fundamental physics is not just about building bigger and bigger machines. It is also about exploring new and more complementary avenues of inquiry. The growing field of astroparticle physics, which uses the universe itself as a laboratory, is providing a new and powerful window onto the fundamental laws of nature. The precision study of the cosmic microwave background, the detection of gravitational waves, the search for high-energy neutrinos from distant astrophysical sources, all of these are providing crucial and often unique clues to the physics that lies beyond our current understanding. The story of our universe, as revealed by the LHC and by all our other scientific explorations, is a story that is still being written. We have learned an immense amount in the last century, but we have also learned the true and vast extent of our own ignorance. We have discovered that the universe we see, the universe of atoms, of stars, of galaxies, is just a tiny 5% fraction of the true cosmic reality. The rest is a dark and largely unknown world of dark matter and dark energy. We have discovered that our universe may have been born from a mysterious and perhaps eternal multiverse. We have discovered that the very fabric of our reality, the space and the time that we inhabit, may be a fragile and perhaps even temporary illusion. These are discoveries that should not lead us to a sense of intellectual despair, but to a feeling of profound and beautiful humility. They are a reminder that we are not the masters of the universe, but are just a small and very young species, just beginning to wake up to the true and breathtaking scale and strangeness of our cosmic home. The quest for knowledge is a long and perhaps infinite one, and the Large Hadron Collider, for all its power and its glory, is just one small step on this grand and unending human adventure, the greatest discoveries, the most profound revelations. The answers to the deepest questions that humanity has ever asked may still lie ahead, waiting for us in the deep, dark, and wonderfully mysterious heart of the subatomic world. The Large Hadron Collider is more than just a powerful machine. It is a symbol of our species' insatiable curiosity, a testament to our relentless drive to understand the fundamental nature of the universe. It is a modern-day cathedral, a place where thousands of scientists from all over the world come together to ask the biggest and most profound questions. And while the LHC has already delivered one of the greatest scientific triumphs of our time, the discovery of the Higgs boson, its work is far from over. The search for answers to the deep, remaining mysteries of the cosmos continues, and the LHC, with its ongoing upgrades and its ever-increasing power, remains at the very forefront of this grand human endeavor. The mystery of dark matter is one of the primary targets of the ongoing LHC program. While the simplest WIMP candidates have not been found, the search has now expanded to a much wider and more diverse range of possibilities. The LHC is searching for the signatures of action-like particles, for the production of sterile neutrinos, for the subtle and often hidden signals of a whole new dark sector of particles and forces. This is a challenging and painstaking search, a process of sifting through a mountain of data for a tiny and often ambiguous signal. But it is a search that is driven by the profound realization that the vast majority of the matter in our universe is still completely unknown to us. The puzzle of the matter-antimatter asymmetry is another, and equally profound, mystery that the LHC is uniquely positioned to address. The LHC-B experiment, one of the 4 large detectors at the LHC, is specifically designed to study the subtle differences in the behavior of matter and antimatter by precisely measuring the decays of particles that contain beauty quarks. Any tiny deviation from the predictions of the standard model in these decays could be the first crucial clue to the new source of CP violation that is needed to explain our own matter-dominated existence. The search for extra hidden dimensions of space is another, and more speculative, but also more exciting, avenue of research at the LHC. The detection of microscopic black holes, or of a tower of heavy Kaluza-Klein particles, would be a discovery of revolutionary and almost unimaginable significance. It would prove that our familiar 4-dimensional reality is just a small slice of a much larger and much more complex multidimensional cosmos, and it would open up a whole new and previously hidden landscape for scientific exploration. The possibility of a multiverse is perhaps the most mind-bending, and also most controversial, of all the ideas that the LHC is capable of probing. While a direct detection of another universe is impossible, the LHC could provide crucial indirect evidence. A discovery of supersymmetry, or of extra dimensions, would lend powerful circumstantial support to the string theory landscape and the Brainworld scenarios, both of which naturally lead to the idea of a multiverse. And the precision measurement of the properties of the Higgs boson could tell us whether our own universe's vacuum is stable or metastable, a clue that could point towards our place in a larger cosmic ensemble of different possible vacuum states. The quest for new physics at the LHC is a quest that is being pushed to new limits by the ambitious and technically challenging high-luminosity LHC upgrade. This is a project that will transform the LHC into an even more powerful discovery machine. A machine that will be able to produce a dataset that is 10 times larger than anything we have collected so far. This huge increase in luminosity, in the number of collisions, will allow physicists to search for extremely rare processes that are simply inaccessible at the current LHC. It will be like turning up the brightness on our picture of the subatomic world, allowing us to see the faint and subtle details that have so far been hidden in the noise. The HL-LHC will be a Higgs factory, producing millions of Higgs bosons and allowing for an incredibly precise measurement of their properties. It will be a dark matter hunter, with a much greater sensitivity to a wide range of dark matter candidates. And it will be a new physics explorer, with the potential to discover new particles, new forces, and new symmetries of nature that could revolutionize our understanding of the universe. But the future of particle physics does not end with the HL-LHC. The global scientific community is already planning for the post-LHC era, for the next generation of even larger and more powerful particle accelerators that will be needed to push the energy frontier even further. The Future Circular Collider is one such proposal, a massive 100-kilometer ring that would be capable of reaching collision energies that are nearly 10 times higher than the LHC. The Compact Linear Collider is another. These are machines that will not be built for decades, but they are a testament to the long-term vision, the ambition, and the enduring curiosity of the human spirit. The search for the fundamental truths of the universe is a long and often difficult journey. It is a journey that is full of both exciting breakthroughs and long periods of patient and sometimes frustrating exploration. And it is a journey that requires a deep and unwavering commitment to the power of science, of reason, of collaboration, to unravel the deep and beautiful secrets of the cosmos. The Large Hadron Collider and the machines that will come after it are more than just scientific instruments. They are symbols of our species' highest aspirations. They are the modern-day pyramids, the cathedrals of our time, monuments to our collective desire to understand our place in the universe, to ask the biggest questions, and to dare to seek the answers. The journey is far from over. The greatest mysteries, the most profound discoveries, the answers to the questions that have haunted humanity since the dawn of consciousness, may still lie ahead, waiting for us in the deep, dark, and wonderfully mysterious heart of the subatomic world.